Everything you see once fit inside a space smaller than an atom. The stars, the galaxies, the light traveling through the void, the atoms in your hand, all of it compressed into a point so impossibly small that the laws of physics we use to describe reality simply collapse. And then, 13.8 billion years ago, it exploded. Not into space. There was no space yet. Space itself was born in that moment, stretching outward faster than light, carrying with it the seeds of every structure, every world, every living thing that would ever exist. This is not a metaphor, this is not poetry, this is what happened. For 380,000 years after that first instant, the universe was a blinding fog. Light could not travel, particles could not form. It was a cosmic soup, so hot and so dense that photons themselves were trapped, scattered endlessly by free electrons in a prison of energy. And then, all at once, the fog cleared, atoms formed, light broke free, and the universe went dark, completely dark. For hundreds of millions of years, there were no stars, no galaxies, just cold hydrogen drifting through an endless night, waiting for gravity to wake it up. But gravity did wake it up. The first stars ignited. Galaxies began to weave themselves into existence. Black holes, the mass of 66 billion suns, tore through the fabric of space-time, and on one unremarkable planet, orbiting one unremarkable star, chemistry became biology, dust became life. Life became you. This is the story of absolutely everything. From the singularity to the last dying ember of light, 100 trillion years from now. Every chapter of existence, every force, every structure, every haunting question we have not yet answered, and it begins where all stories must, at the very beginning. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe had a birthday, 8 billion years ago, give or take about 200 million years. Everything that has ever existed or ever will exist appeared. Not in a place, not at a location you could point to on a map. There was no map. There was no space to put a map in. There wasn't even a concept of direction or distance or time. And then, suddenly there was. This is not a metaphor. This is not poetic language. This happened. The entire observable universe, every galaxy, every star, every planet, every atom in your body, all of it came from a state so compressed, so dense, so hot, that the laws of physics as we understand them simply stop working. Scientists call it the initial singularity, and it is the most honest name they could come up with, because singularity in physics is just a polite way of saying we have absolutely no idea what we're talking about. The equations break, the math returns infinity. The models throw up their hands and walk away. Everything we know about how matter and energy and space-time behave collapses into a single point of ignorance so profound that even calling it a point is probably wrong. A point implies a location. A location implies space. There was no space, not yet. And then the Big Bang happened. Except it wasn't a bang. There was no sound. There was no explosion in the sense you're picturing. It wasn't a bomb going off in an empty room. It was the room itself coming into existence. Space didn't expand into something. Space itself expanded, pulling everything with it, creating distance where there had been none. If you've ever heard someone describe the Big Bang as the universe exploding outward from a single point in space, they're wrong. The Big Bang happened everywhere simultaneously. Every point in the universe today was, At that initial moment, the same point. There was no center, there was no edge, there still isn't. You are sitting right now at the exact spot where the Big Bang occurred. So is everyone else. This is the part where most explanations stop and let you sit with the headache. But the headache is the point. The beginning of the universe is not supposed to make intuitive sense. Your brain evolved to throw rocks at animals and recognize faces in shadows. It was not built to visualize the origin of space-time. The fact that we can describe this process with math at all, the fact that we can rewind the clock and predict what the universe looked like when it was a fraction of a second old, is one of the most staggering achievements in the history of human thought. It just doesn't feel staggering because we've gotten used to it. So let's go back, all the way back, to the very first moment we can talk about with any confidence. At roughly 1/1,000,000,000 of a trillionth of a trillionth of a second after the initial singularity, something extraordinary happened. The universe underwent a period of expansion so violent, so fast, that it makes every explosion you've ever heard of look like a polite cough. This is cosmic inflation, and it is the reason the universe looks the way it does today. Alan Guth, a physicist at MIT, proposed the idea in 1980, and it solved several major problems in cosmology all at once. Before inflation, scientists couldn't explain why the universe looked so smooth. Why distant regions of space that should never have been able to communicate with each other, regions separated by distances light itself couldn't have crossed in the age of the universe, somehow had the same temperature, the same density, the same properties. It was as if you walked into two completely isolated rooms on opposite sides of the planet and found them decorated identically down to the position of the furniture. That doesn't happen by coincidence. Something must have connected them. Inflation was the answer. In a span of time so short that writing it out in normal numbers is almost meaningless, somewhere around 10 to the negative 32 seconds, the universe doubled in size at least 60 times, possibly more, possibly a lot more. Imagine a basketball inflating to the size of the observable universe in less time than it takes light to cross the nucleus of an atom, except faster. Because for that brief fraction of a moment, the expansion exceeded the speed of light. That's allowed, by the way. Nothing can move through space faster than light, but space itself has no speed limit. Space can expand as fast as it wants, dragging everything embedded in it along for the ride. And during inflation, space expanded so fast that regions of the universe that had been in contact, that had been part of the same smooth initial conditions, were suddenly flung apart to distances so vast that they would never see each other again. That's why the universe looks smooth. It's not that distant regions coincidentally have the same properties. It's that they used to be the same place. The energy driving inflation came from something called the inflaton field, a hypothetical field that hasn't been directly detected but is the leading explanation for what could generate that kind of expansion. Think of it as a temporary source of pressure built into the fabric of space itself. When the inflaton field decayed, all that energy had to go somewhere. It dumped into the universe as radiation and particles, reheating the cosmos and kicking off the hot, dense phase we usually associate with the Big Bang. This is the moment, right after inflation ended, where the universe became something we can describe in detail. It was hot. Not hot like a fire or a furnace, hot in a way that obliterates the concept of solid matter entirely. Temperatures sat somewhere around 18 billion degrees Fahrenheit, and at that temperature, atoms don't exist, molecules don't exist, even protons and neutrons don't exist yet. What you have instead is a seething, roiling bath of subatomic particles and energy, a cosmic soup where quarks and leptons and photons slam into each other trillions of times per second, fusing, splitting, annihilating, reforming. The forces we know today, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, had not yet separated into distinct entities. In the first moments after inflation, they were unified. As the universe expanded and cooled, those forces began to peel apart one by one, like layers of meaning separating out of a single word. Gravity split off first, almost immediately. Then the strong nuclear force, the glue that holds atomic nuclei together. Then electromagnetism and the weak force which governs radioactive decay. By the time the universe was about 1 picosecond old, 1/1,000,000th of a second, the four fundamental forces had settled into the roles they still play today. And the particles that make up all ordinary matter, quarks and leptons, were swimming freely in a plasma so dense and so energetic that light couldn't travel more than a microscopic distance before smashing into something else. Quarks are the building blocks of protons and neutrons. There are 6 types, though only 2 matter for our story: up quarks and down quarks. 3 quarks stuck together make a proton or a neutron. 2 up quarks and 1 down quark make a proton. 1 up quark and 2 down quarks make a neutron. Simple rules, but in this early universe, it was too hot for quarks to stick together. They bounced around independently, colliding with electrons, neutrinos, and photons in a chaotic mess that had no structure beyond raw energy. Then the universe kept expanding, and as it expanded, it cooled. By the time it reached about 1 microsecond old, 1/1,000,000th of a second, the temperature had dropped enough for quarks to start binding together. Protons and neutrons began to form. This is called the quark epoch, and it's the moment when the fundamental building blocks of atomic nuclei came into existence. Still no atoms, though. The universe was still far too hot for electrons to settle into orbit around nuclei. Any electron that tried was immediately blasted away by a passing photon. The cosmos at this stage was opaque, a glowing fog where light couldn't travel in straight lines because it was constantly scattering off free electrons. If you could somehow stand inside this universe, which you couldn't because you would be disassembled into component particles instantly, you wouldn't see anything. Not because it was dark, because it was too bright. Every direction you looked would be a wall of light, blinding and impenetrable. And that's how things stayed for a very, very long time. Well, a very long time by the standards of the first second. Which, to be clear, was an eventful second. At 1 second old, the universe had cooled to about 10 billion degrees. Still unimaginably hot, but cool enough for protons and neutrons to start thinking about sticking together. At around 3 minutes, the temperature dropped below 1 billion degrees and nuclear fusion became possible. Protons began fusing with neutrons to form the nuclei of the lightest elements. Mostly hydrogen, which is just a single proton. Some helium, which is 2 protons and 2 neutrons. Traces of deuterium, a heavy version of hydrogen with an extra neutron. Even smaller amounts of lithium. This period is called Big Bang nuclear synthesis, and it lasted for about 17 minutes. By the time it was over, roughly 75% of the universe's ordinary matter was hydrogen, and 25% was helium, with everything else making up a rounding error. That ratio, that 75-25 split, is one of the strongest pieces of evidence we have that the Big Bang actually happened. Because when astronomers look at the oldest stars and gas clouds in the universe, the ones that formed before anything else had a chance to pollute them with heavier elements, they find exactly that ratio. 75% hydrogen, 25% helium. The match is so precise it's almost eerie. But there's a catch. Those nuclei, the hydrogen and helium cores that formed in the first few minutes, they weren't atoms yet. They were just bare nuclei, positively charged particles drifting through a sea of free electrons and photons. And they would stay that way for a long time. The universe had to cool a lot more before electrons could settle down. There's a specific temperature where this happens, where the universe becomes cool enough for electrons to bind to nuclei and form neutral atoms. That temperature is about 3000 degrees Kelvin, and the universe reached it roughly 380,000 years after the Big Bang. Not 3 minutes, not 3 hours, 380,000 years. For more than a third of a million years, the universe was a glowing plasma, a fog of charged particles that trapped light in an endless game of pinball. Then the fog cleared. When electrons finally combined with nuclei to make atoms, something remarkable happened. Photons, the particles of light, suddenly had nothing to scatter off of. Neutral atoms don't interact with light the same way charged particles do. The universe went from opaque to transparent almost instantly. Light that had been trapped, bouncing endlessly from particle to particle, was suddenly free to travel in straight lines. It began moving outward through space, and it has been traveling ever since. That light is still here. We can see it. It's called the cosmic microwave background, and it is the oldest light in the universe. When we point our telescopes at the sky and tune them to the right frequency, we are looking at photons that have been traveling toward us for 13.8 billion years. We are seeing the universe as it looked 380,000 years after it began, a snapshot of the moment the lights came on. The cosmic microwave background is not optional. It's not a detail that might or might not support the Big Bang. It is the smoking gun. Every prediction the Big Bang model makes about the early universe, the temperature, the uniformity, the tiny fluctuations in density that would later seed galaxies, all of it shows up in the CMB exactly as predicted. When Arno Penzias and Robert Wilson discovered it in 1964, they didn't know what they were looking at. They thought it was noise. They thought it might be interference from New York City. They thought it might be bird droppings on their antenna. They cleaned the antenna. The signal didn't go away, because it wasn't coming from the antenna. It was coming from the sky. It was coming from everywhere. That uniformity is important. The cosmic microwave background looks almost exactly the same in every direction. Almost. There are tiny variations, temperature differences of about 1 part in 100,000, and those variations are the seeds of everything that came after. Regions that were slightly denser than average had slightly stronger gravity. They pulled in more matter. Over time, those tiny overdensities grew into the galaxies, stars and planets we see today. If the early universe had been perfectly smooth, nothing would have formed. We wouldn't be here. The fact that we exist at all is proof that the universe was just barely lumpy enough. So let's take stock. In the first 3 minutes, the universe went from a state of unimaginable density and heat to a cooling plasma of hydrogen and helium nuclei. In the next 380,000 years, it cooled further until atoms could form and light could travel freely. And from that point forward, the universe we recognize, the universe of stars and galaxies and structure, became possible. But it didn't happen right away. For a long time after the cosmic microwave background was released, the universe was dark. There were no stars yet. The hydrogen and helium gas drifting through space was neutral and cold, invisible except for the faint glow of the CMB itself, which was steadily redshifting into the infrared as the universe expanded. This period is called the Cosmic Dark Ages, and it lasted for tens of millions of years, possibly more than 100 million. Nothing was happening. Or rather, nothing visible was happening. But beneath the surface, gravity was working. Those tiny overdensities in the early universe were pulling gas into clumps. Dark matter, which doesn't interact with light but does have gravity, was collapsing into halos, and inside those halos, ordinary matter was beginning to gather. Slowly, patiently, invisibly, the universe was setting the stage for the next act. The one where the first stars would ignite and the cosmic dark ages would end. The universe was still screaming. At 1 second old, it had calmed down enough for protons and neutrons to exist. At 3 minutes, those particles started sticking together, but the universe itself was still far too violent for anything resembling calm. If you could somehow pause time at that moment and take a snapshot, you wouldn't see galaxies or stars or planets. You wouldn't see atoms. You would see a churning ocean of subatomic wreckage, a cosmic soup so hot and so dense that light itself couldn't escape. This wasn't a metaphor. This was the actual state of the universe for the first 380,000 years of its existence. A glowing fog where photons, the particles that carry light, were trapped in an endless loop of collisions. They couldn't travel more than a microscopic distance before smashing into something else, bouncing off, and getting absorbed again. The universe was blinding and opaque at the same time, a wall of light you couldn't see through. Scientists call this period the photon epoch, though that name makes it sound calmer than it was. A better name might be the cosmic traffic jam. Every photon trying to move forward, every electron in the way, every collision scattering the light in a new direction. Imagine trying to walk through a crowd so packed that every step forward requires shoving past a dozen people. Now imagine you're made of light. Now imagine the crowd is made of charged particles that grab you every time you get close. That's what the early universe was like for photons. They were stuck. The reason comes down to a specific kind of matter that dominated the universe at this stage. Not solid matter, not gas, plasma. A plasma is what you get when you heat a gas so much that electrons get ripped away from their nuclei. What's left is a sea of free-floating charged particles, positive nuclei on one side, negative electrons on the other, all of them bouncing around independently. Plasma doesn't behave like a gas. It conducts electricity. It responds to magnetic fields, and critically, it interacts very, very strongly with light. Every time a photon in the early universe tried to travel through this plasma, it hit a free electron. The electron absorbed the photon, got a little kick of energy, and then spat the photon back out in a random direction. This process is called Thomson scattering, and it's the reason the early universe stayed opaque. The photons were there, the light was there, it just couldn't go anywhere. It was trapped inside a fog made of its own interactions. That fog was everywhere. There was no edge to it. There was no clear spot. The entire observable universe, every cubic centimeter of space, was filled with this hot, dense plasma. You couldn't see more than a fraction of a millimeter in any direction before the light scattered into chaos. If you've ever been in a thick fog at night, where the headlights of your car just bounce back into your eyes, you've experienced a tiny echo of what this was like. Except instead of water droplets scattering the light, it was free electrons. And instead of your car, it was the entire universe. And inside that fog, something remarkable was happening. The universe was cooking. Let's rewind for a moment to the very first microsecond. At that point, the universe wasn't just hot. It was so hot that protons and neutrons couldn't exist. What you had instead was something even more fundamental: quarks. Quarks are the building blocks of protons and neutrons, and in the first moments after inflation, they were swimming freely in a state of matter that has no analog in the world you experience. Scientists call it a quark-gluon plasma, and it is one of the strangest substances physics has ever predicted. Here's what makes it strange. Normally, quarks are locked inside protons and neutrons by the strong nuclear force, the glue that holds atomic nuclei together. You can't pull a quark out of a proton any more than you can pull a single thread out of a woven carpet without unraveling the whole thing. The strong force gets stronger the farther apart you try to pull quarks, which means isolating one takes so much energy that you just end up creating new quarks instead. Quarks are prisoners of their own interactions. But in the first microsecond, the universe was so hot that the strong force couldn't hold them. The quarks and gluons, the particles that carry the strong force, were free to move independently. They formed a kind of liquid, a fluid of the most fundamental particles we know, sloshing around at temperatures that would make the core of a star look like a freezer. How hot are we talking? Over 4 trillion degrees Celsius. That number is hard to grasp, so here's a comparison. The core of our Sun sits at about 15 million degrees. The quark-gluon plasma was more than 250,000 times hotter than that. At those temperatures, nothing we would recognize as matter could exist. Atoms, molecules, even the concept of a solid object, all of it would be vaporized instantly. And here's the part that blew physicists' minds when they finally managed to recreate this stuff in the lab. The quark-gluon plasma didn't behave like a gas, it behaved like a liquid. Not just any liquid. A nearly perfect liquid, one with almost no viscosity. When physicists at CERN and Brookhaven National Laboratory smashed heavy ions together at nearly the speed of light, they expected the resulting quark-gluon plasma to spray outward like shrapnel from an explosion. It didn't. It flowed. It formed droplets. It produced wakes and splashes, the way water does when you drag your hand through it. Quarks moving through this primordial soup left trails behind them, patterns of disturbed flow that looked eerily similar to a boat cutting through a lake. One researcher described it as the universe's first fluid dynamics experiment. Another said it was like watching the cosmos learn how to pour. The quark-gluon plasma wasn't just a state of matter. It was the hottest liquid that has ever existed, and for a brief moment it was all there was. Then the universe expanded, and as it expanded, it cooled. By the time the universe was about 1 microsecond old, the temperature had dropped below 2 trillion degrees, and that was cool enough for quarks to start binding together. The quark-gluon plasma froze, not into ice, but into protons and neutrons. 3 quarks snapped together to make each one. 2 up quarks and 1 down quark formed a proton. 1 up quark and 2 down quarks formed a neutron. The building blocks of atomic nuclei had arrived. Still no atoms, though. The universe was still far too hot for that. What you had now was a sea of protons, neutrons, electrons, and photons, all bouncing off each other in a state of barely controlled chaos. The temperature was still in the billions of degrees. Any structure more complex than a lone proton was immediately torn apart by the surrounding radiation. But the clock was ticking down. At around 3 minutes old, the universe cooled to about 1 billion degrees. That might still sound hot, and it is, but it's cool enough for something critical to happen: nuclear fusion. The same process that powers stars was about to happen everywhere at once, across the entire universe, all in the span of about 17 minutes. Protons and neutrons, slamming into each other in the heat, began to stick. A proton and a neutron fused to form deuterium, a heavy version of hydrogen with 1 proton and 1 neutron in its nucleus. 2 deuterium nuclei collided and fused into helium-4, the most common form of helium, with 2 protons and 2 neutrons. Some tritium formed, a radioactive isotope of hydrogen with 1 proton and 2 neutrons. Trace amounts of lithium-7 appeared, the lightest metal in the universe, with 3 protons and 4 neutrons. This process is called Big Bang nucleosynthesis, and it is one of the most important 17 minutes in the history of existence. By the time it was over, the universe had settled into a composition that would remain mostly unchanged for billions of years. Roughly 75% hydrogen, 25% helium, and a tiny sliver of everything else. That ratio is not a guess. It's a prediction, one that the Big Bang model made decades before we had the tools to test it properly. And when astronomers finally looked at the oldest stars and gas clouds in the universe, the ones that formed before anything else had a chance to pollute them, they found exactly that ratio. 75% hydrogen, 25% helium. The match is so precise, it's almost unsettling. It's as if the universe left us a receipt. But here's the thing. Those nuclei, the hydrogen and helium cores that formed in the first few minutes, they weren't atoms yet. They were just bare nuclei, positively charged particles drifting through a sea of free electrons and photons. And they stayed that way for a very, very long time. Because the universe, even after nucleosynthesis, was still too hot for electrons to settle down. Electrons are light, they're easy to knock around. And in a universe filled with high-energy photons, every time an electron tried to bind to a nucleus to form a neutral atom, a passing photon would smack it loose again. It was like trying to build a house in a hurricane. The materials were there, the blueprints were ready, but the conditions wouldn't allow it. So the universe stayed as a plasma, a hot ionized fog of nuclei, electrons and photons, all interacting constantly. The photons couldn't escape. The light was trapped. The universe was opaque. And this is how things remained for the next 380,000 years. That's a long time. Long enough for the universe to expand considerably. Long enough for the temperature to drop from billions of degrees to a few thousand. Long enough for the density to thin out, for the particles to spread farther apart, for the wild chaos of the first few minutes to settle into something that looked, if you squinted, almost calm. But it was still a fog, still opaque, still glowing. Then, finally, the universe cooled enough. At around 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees Kelvin, and at that specific temperature, something remarkable happened. Electrons began to stick. This moment is called recombination, though the name is misleading because the electrons and nuclei had never been combined before. A better name might be first combination, but science is stuck with the term it picked, so recombination it is. What matters is what happened next. As electrons bound to nuclei to form neutral atoms, the fog cleared. Here's why. A neutral atom doesn't scatter light the same way a free electron does. Photons can pass through a gas of neutral atoms with relatively little interaction. There are still some collisions, some absorption and re-emission, but nowhere near the constant barrage that was happening before. When the universe transitioned from a plasma of free electrons to a gas of neutral hydrogen and helium atoms, the photons that had been trapped for 380,000 years were suddenly free to travel. They began moving outward through space in straight lines, and they've been moving ever since. That light is still here. We can still see it. It's called the cosmic microwave background, and it is the oldest light in the universe. When we point our telescopes at the sky and tune them to microwave frequencies, we are looking at photons that were released 380,000 years after the Big Bang. We are seeing the universe as it looked at the moment the fog lifted. a snapshot of the infant cosmos, frozen in radiation. The cosmic microwave background was discovered in 1964 by two radio astronomers named Arno Penzias and Robert Wilson. They were trying to eliminate noise from a large antenna at Bell Labs in New Jersey when they kept picking up a faint hiss that wouldn't go away. They checked the equipment. They cleaned the antenna. They even shooed away pigeons that had been nesting inside, thinking bird droppings might be the source of the interference. The signal didn't budge. It took them a while to realize they weren't looking at noise. They were looking at the universe. The hiss was coming from every direction in the sky, uniformly, constantly. It was the afterglow of the Big Bang, stretched and redshifted by 13.8 billion years of cosmic expansion. Penzias and Wilson won the Nobel Prize for their discovery, and cosmology was never the same. The cosmic microwave background is not optional. It's not a detail that might or might not support the Big Bang. It is the smoking gun. Every prediction the Big Bang model makes about the early universe shows up in the CMB exactly as expected. The temperature, the uniformity, the tiny ripples in density that would later seed galaxies, all of it is there. If the Big Bang didn't happen, the CMB wouldn't exist. The fact that we can see it, measure it, map it in exquisite detail is one of the most powerful confirmations of the entire theory. And those tiny ripples matter. The cosmic microwave background looks almost perfectly smooth. Almost. There are variations in temperature of about 1 part in 100,000, regions that were slightly hotter, regions that were slightly cooler. Those differences trace back to tiny fluctuations in the density of matter in the early universe. Places where there was slightly more stuff, and places where there was slightly less. Gravity doesn't care about smooth. Gravity cares about clumps. Regions that were even a tiny bit denser than average had slightly stronger gravity. They pulled in more matter. Over time, those overdensities grew. They became the seeds of galaxies. They became the seeds of galaxy clusters. They became the seeds of the large-scale structure we see in the universe today. If the early universe had been perfectly smooth, nothing would have formed. No stars, no planets, no people. The fact that we exist at all is proof that the universe was just barely lumpy enough. So let's take stock. In the first microsecond, the universe was a quark-gluon plasma, the hottest liquid that ever existed, flowing and splashing in ways that defy everyday intuition. In the first 3 minutes, protons and neutrons formed and immediately began fusing into the lightest elements. For the next 380,000 years, the universe was an opaque fog, a glowing plasma where light couldn't travel more than a fraction of a millimeter before scattering off a free electron. Then, at 380,000 years, electrons combined with nuclei to form neutral atoms. The fog cleared, the light escaped, and the cosmic microwave background was born. That moment, that transition from opaque plasma to transparent gas, was one of the most important events in cosmic history. It marked the end of the universe's infancy, the end of the time when light was trapped, the end of the photon epoch. From that point forward, the universe was dark. Not dark because there was no light, dark because there were no stars. The hydrogen and helium gas drifting through space was neutral and cold, invisible except for the faint glow of the cosmic microwave background itself, which was steadily redshifting into the infrared as the universe expanded. For tens of millions of years, possibly more than 100 million, nothing glowed, nothing burned, nothing shone. This is the period astronomers call the cosmic dark ages, and it is the next chapter of the story. A long, quiet stretch of time when the universe was waiting for gravity to pull the gas into clumps, waiting for those clumps to collapse, waiting for the first stars to ignite and the darkness to end. The universe went dark. Not the kind of dark you get when you close your eyes or when the power goes out. Not the dark of a basement or a cave or the bottom of the ocean. This was a different kind of absence. The kind where there's nothing to see because there's nothing making light. For tens of millions of years, possibly more than 100 million, the universe sat in a state of near total darkness, waiting for something to happen. This is the cosmic dark ages, and calling it dark is almost too generous. The universe wasn't empty, it was full of stuff. Hydrogen and helium gas drifted through space in vast invisible clouds. Dark matter, whatever that actually is, had already started clumping into halos under the pull of gravity. The cosmic microwave background was still there, glowing faintly in every direction, though by this point it had redshifted so far into the infrared that calling it a glow is a stretch. If you could somehow stand in the middle of this universe, which you couldn't because you would freeze instantly and also suffocate, and also there was nowhere to stand, you wouldn't see anything, no stars, no galaxies, no light sources of any kind except the dimmest possible afterglow of the Big Bang itself, fading steadily as space expanded. The Dark Ages began the moment the cosmic microwave background was released. That moment, roughly 380,000 years after the Big Bang, marked the transition from an opaque plasma to a transparent gas. The fog cleared, the photons escaped, and the universe, for the first time in its history, became see-through, except there was nothing to see. The atoms that had just formed, hydrogen and helium mostly, were neutral. They didn't emit light, they didn't glow. They just drifted, cold and invisible, through an expanding void. This wasn't supposed to last forever. The universe had a plan, encoded in the tiny ripples left over from inflation. Those ripples, the quantum fluctuations that got stretched to cosmic scales during the first trillionth of a second, were still there. They showed up as slight variations in the density of matter. Places where there was a little more hydrogen, places where there was a little less. The differences were tiny, about 1 part in 100,000, but they were enough. Because gravity doesn't need much. Gravity is patient. Give it a small advantage, and it will amplify that advantage over time until the small becomes enormous. Here's how it worked. In regions where the density was even slightly higher than average, gravity was slightly stronger. That stronger gravity pulled in more matter from the surrounding space. As more matter fell in, the gravity got stronger still, which pulled in even more matter. A feedback loop, slow at first, but accelerating. Meanwhile, regions that started out slightly underdense lost matter to their denser neighbors. They became voids. Over millions of years, the smooth universe of the Dark Ages began to develop structure. Not visible structure, not yet, but gravitational structure. The seeds of galaxies were growing in the dark. The first structures to form weren't galaxies in any sense we'd recognize. They were dark matter halos. Dark matter, whatever it is, doesn't interact with light or ordinary matter except through gravity. It doesn't collide, it doesn't bounce, it doesn't heat up or cool down. It just falls. And because it only interacts gravitationally, dark matter started clumping together earlier and faster than ordinary matter. By the time the universe was a few tens of millions of years old, dark matter had already collapsed into dense halos, invisible gravitational wells scattered throughout space. Ordinary matter, the hydrogen and helium gas, fell into those wells. It didn't have a choice. Gravity pulled it in. But ordinary matter is messier than dark matter. When gas clouds collide, they don't pass through each other like dark matter does. They crash, they heat up, they radiate energy. They lose momentum and settle into the center of the halo, pooling at the bottom of the gravitational well like water collecting at the lowest point of a valley. This is how the first proto-galaxies formed. Not as galaxies yet, not as anything you could see, but as dense clumps of gas sitting inside dark matter halos, waiting for the next step. The next step was collapse. The gas clouds were massive, hundreds of thousands or even millions of times the mass of our Sun, but they were spread out over huge volumes of space. For a star to form, that gas has to compress. It has to squeeze down into a region small enough and dense enough that the pressure and temperature at the center can ignite nuclear fusion. That takes time. It takes gravity working slowly, pulling the gas inward, shrinking the cloud, concentrating the mass. But there was a problem. Gas doesn't like to collapse. When you squeeze gas, it heats up, and when gas heats up, the pressure inside it rises. That pressure pushes outward, resisting the inward pull of gravity. For a cloud to collapse all the way down to the point where a star can form, it needs a way to get rid of that heat. It needs to cool down. In the modern universe, gas clouds cool by radiating energy away in the form of infrared light. Molecules like carbon monoxide and water vapor are very good at this. They absorb thermal energy and spit it out as photons, which then escape into space, carrying the heat with them. The cloud cools, the pressure drops, and gravity wins. The problem in the early universe was that those molecules didn't exist yet. Carbon monoxide requires carbon, water vapor requires oxygen. Neither of those elements had been made. The only things available were hydrogen and helium, and neither of those is particularly good at cooling. Hydrogen can radiate energy, but only under specific conditions, and the process is slow. Helium barely interacts with anything, so the first gas clouds trying to collapse were doing it the hard way, with almost no help. This is why the first stars took so long to form. The universe had to wait for gravity to win a war against pressure, using only the weakest possible cooling mechanisms. Current estimates suggest the first stars ignited somewhere between 100 and 250 million years after the Big Bang. That's a wide range because we don't know exactly when it happened. We've never directly observed a first-generation star. They're all gone now, dead for billions of years. What we have instead are models, simulations, and a handful of indirect clues. When the first stars finally did ignite, they were unlike anything that came after. Astronomers call them population 3 stars, a name that makes no intuitive sense until you realize the naming system was invented backward. Population I stars are the youngest, the ones forming today in places like the Orion Nebula, full of heavy elements. Population 2 stars are older, found in globular clusters, with fewer heavy elements but still some. Population 3 stars are the first, the ones with no heavy elements at all, because there hadn't been time for any to form yet. Pure hydrogen and helium, nothing else, and they were enormous. Without heavy elements to help the gas cool, the first collapsing clouds had to be much more massive than modern star-forming regions just to overcome the pressure. The result was stars weighing anywhere from 100 to perhaps 300 times the mass of our Sun. For comparison, the largest stars we've found in the Milky Way today top out around 200 solar masses, and even those are rare. Population 3 stars were all giants. Big stars burn fast. The more massive a star is, the hotter its core, and the faster it fuses hydrogen into helium. A star like our Sun will burn steadily for about 10 billion years. A star weighing 100 solar masses might last only 2 or 3 million years. Population 3 stars lived fast, burned bright, and died young. Most of them likely ended their lives in supernovae, violent explosions that scattered the first heavy elements into space. Carbon, oxygen, nitrogen, iron, all the elements that didn't exist before, suddenly seeded into the surrounding gas. That enriched gas would go on to form the next generation of stars, population 2 stars, which could cool more efficiently and form at lower masses. The cycle had begun. But the first stars did something else, something that changed the universe permanently. They produced light, a lot of it, and not just any light. Ultraviolet light, high-energy photons capable of ripping electrons off hydrogen atoms, ionizing them, turning neutral hydrogen back into a plasma. This process is called reionization, and it marks the end of the Dark Ages. Here's what happened. As the first stars ignited, they flooded their surroundings with ultraviolet radiation. That radiation slammed into the neutral hydrogen gas, filling the space between stars, ionizing it, creating bubbles of ionized gas around each new star. At first, those bubbles were small, isolated pockets of light in an otherwise dark universe. But as more stars formed, more bubbles appeared. The bubbles grew, they merged. Slowly, unevenly, over the course of hundreds of millions of years, the ionized regions expanded outward, eating into the neutral hydrogen, spreading the light farther and farther. By about 550 million years after the Big Bang, significant portions of the universe had been reionized. By around 1 billion years, the process was mostly complete. The neutral hydrogen that had filled the universe during the Dark Ages was gone, converted back into a plasma, though a much thinner and cooler plasma than the one that existed before recombination. The universe had come full circle, in a sense. It started as a plasma, cooled into a neutral gas, and then heated back up into a plasma again. Except this time, the plasma was filled with stars. Reionization wasn't a single moment. It was a messy, drawn-out process that happened at different rates in different places. Some regions of the universe reionized early, wherever the first stars happened to form. Other regions stayed neutral longer, the last pockets of darkness holding out until the light finally reached them. The James Webb Space Telescope has been searching for galaxies from this era, trying to map out when and where reionization happened. What it's found is a universe in transition, patchy and uneven, with some regions glowing bright and others still dark. The end of the Dark Ages didn't happen all at once. There was no single switch that turned the lights on. It was more like a slow sunrise spreading across a planet, starting in a few isolated spots and gradually covering everything. And even after reionization, the universe was still mostly empty. The stars that ended the Dark Ages were scattered, isolated, separated by vast distances. The first galaxies were just beginning to take shape, loose collections of stars bound together by gravity. Nothing like the grand spirals and ellipticals we see today, but the foundation was there. The seeds had germinated. The universe had figured out how to make light. There's a subtlety here worth pausing on. The term Dark Ages is relative. The universe wasn't literally dark in every sense. It was still full of infrared radiation from the cooling cosmic microwave background. It was full of the faint 21-centimeter radio emission from neutral hydrogen, a wavelength produced when the spin of a hydrogen atom's electron flips relative to its nucleus. If you had eyes that could see in radio waves or infrared, the Dark Ages universe would have been faintly glowing, not bright, but not completely invisible either. The darkness was specific to visible light, the light human eyes can see. And that matters because when astronomers talk about the Dark Ages, they're really talking about the absence of stars, the absence of the kind of light that makes the universe interesting. The first stars didn't just end the Dark Ages, They fundamentally changed what the universe could do. Before population 3 stars, the universe was a 2-ingredient system: hydrogen and helium. That's it. No carbon for life. No oxygen for water. No silicon for rocks. No iron for planetary cores. Every element heavier than helium was made inside stars or in the explosions that ended those stars' lives. The first supernovae were the first factories. They took hydrogen and helium and cooked it under unimaginable heat and pressure into everything else. When they exploded, they distributed that everything else into space, polluting the surrounding gas with the raw materials for planets, for chemistry, for complexity. This is not optional. Every atom in your body heavier than hydrogen was forged in a star or a supernova. The carbon in your DNA, the oxygen in your lungs, the calcium in your bones, the iron in your blood, all of it came from stars that died billions of years ago. You are not just in the universe, you are made of it. And the process that made you began with the first population 3 stars exploding in the Dark Ages. There's something poetic about that, though the universe doesn't care about poetry. It cares about gravity and pressure and nuclear fusion rates. The fact that those impersonal physical processes eventually led to living things capable of looking back at the stars and figuring out where they came from is an accident. A beautiful accident maybe, but an accident nonetheless. The universe wasn't trying to make you. It was just following the rules of gravity and thermodynamics, and you happened to fall out of the math. Still, the Dark Ages matter. They were the hinge point between the simple universe of the Big Bang and the complex universe we see today. Before the Dark Ages, the universe was uniform, smooth, boring. After the Dark Ages, it was full of structure. Stars, galaxies, clusters, voids, filaments, all of it built on the tiny quantum ripples that inflation left behind. The Dark Ages were the waiting room, the moment when the seeds of structure were planted and gravity began the slow work of turning them into forests. And the first stars were just the beginning. Once they proved that collapse was possible, that gas could gather and compress and ignite, the floodgates opened. More stars formed. Those stars grouped into galaxies. The galaxies grouped into clusters. The clusters strung themselves along filaments of dark matter, forming the cosmic web, the largest structure in the universe. All of it growing, branching, spreading outward from the tiny overdensities left over from the first moments after the Big Bang. The Dark Ages lasted somewhere between 100 million and a few 100 million years, depending on how you measure them. That might sound like a long time. In cosmic terms, it's a blink. The universe today is nearly 14 billion years old. The Dark Ages represent less than 2% of that history. A brief intermission between the blinding light of the Big Bang and the slow construction of galaxies. But it was a necessary intermission. Without it, there would be no structure, no stars, no us. By the time reionization was complete, the universe was unrecognizable compared to the smooth fog of the recombination era. It was full of light, full of activity, full of newborn galaxies pulling themselves together out of the primordial gas. The first chapter of cosmic history had closed. The second was just beginning. And the structures forming in the aftermath of the Dark Ages, the galaxies and clusters taking shape across billions of light years, would become the framework for everything that followed. The first stars didn't stay alone for long. Gravity won't allow it. Give gravity a few million years, a cloud of gas, and something to pull toward, and it will build you a galaxy, not all at once, not neatly, but eventually. The universe had just ended the Dark Ages. The first population 3 stars had ignited, lived, and exploded, scattering the first heavy elements into space. And now, roughly 500 million years after the Big Bang, something new was starting to happen. The isolated pockets of light scattered across the cosmos were beginning to clump together. Stars were finding each other, gas clouds were merging, dark matter halos were colliding and growing. The universe was organizing itself into the largest structures it would ever build, galaxies. A galaxy is not just a collection of stars, it's a gravitationally bound system, a piece of the universe that has decided to stay together despite the expansion of space trying to pull everything apart. Most galaxies contain anywhere from a few thousand stars to several trillion, spread across distances ranging from a few hundred light-years to over 1 million. They come in different shapes. Spirals with elegant arms curving outward from a central bulge, ellipticals that look like smooth glowing footballs with no clear structure, irregulars that have no symmetry at all, just chaotic clouds of stars and gas shaped by collisions or tidal forces. The observable universe today contains somewhere between 200 billion and 2 trillion of them. That number has error bars the size of entire galaxy clusters, which tells you how hard it is to count something when you can't see most of it and the thing you're counting keeps moving. The question is not whether galaxies exist. We can see them. The question is how they got here. How did the universe go from a smooth fog of hydrogen and helium to a cosmos filled with spiral arms, supermassive black holes, and structures so large they span hundreds of millions of light-years? The short answer is gravity and time. The longer answer requires dark matter, collisions, and a process so messy it's still being argued about in conference rooms full of cosmologists who can't agree on the details. Let's start with the framework. The leading model of how galaxies form is called lambda CDM, which stands for lambda cold dark matter. Lambda represents dark energy, the mysterious force accelerating the expansion of the universe. CDM represents cold dark matter, a hypothetical form of matter that doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter except through gravity, and makes up roughly 85% of all the matter in the universe. If that sounds like a placeholder for something we don't understand, that's because it is. Dark matter is the name scientists gave to the missing mass they know has to be there, because without it, the galaxies we see wouldn't hold together. Stars orbit galactic centers too fast. Galaxies in clusters move too quickly. The gravity from visible matter isn't enough to explain what we observe. So there must be something else, something invisible, something that only pulls. In the lambda CDM model, the universe starts with tiny fluctuations in density left over from inflation. Those fluctuations were imprinted in the cosmic microwave background, and they seeded everything that came after. Regions that were slightly denser than average had slightly stronger gravity. Dark matter, because it doesn't collide with anything, started collapsing into those overdense regions earlier and faster than ordinary matter. By the time the first stars were forming, dark matter had already built the scaffolding, halos, invisible wells of gravity scattered throughout the young universe, waiting for gas to fall in. Ordinary matter followed. Hydrogen and helium clouds drifted toward the densest regions, pulled by the gravity of the dark matter halos. As the gas fell inward, it heated up from compression. Some of that heat radiated away, allowing the gas to cool and settle toward the center of the halo. Once enough gas collected in one place, it began to fragment into clumps. Those clumps collapsed further. Stars ignited. A galaxy was born. That's the clean version. The real process was a lot messier. Early galaxies were not the grand spirals we see in Hubble photos. They were small, chaotic, and violent. A typical early galaxy might have contained only a few million stars, a fraction of the 100 billion stars in the Milky Way today. These proto-galaxies formed wherever dark matter halos were dense enough to pull in gas. And because the early universe was more crowded, those halos were close together, close enough to interact, close enough to collide, close enough to merge. Galaxy mergers are one of the primary engines of galactic evolution. When two galaxies collide, their stars almost never hit each other. Space is too empty. The distances between stars are so vast that even during a collision, the odds of two stars actually smashing together are vanishingly small. What does collide is the gas. Gas clouds slam into each other, shock, compress, and ignite in massive bursts of star formation. The collision can strip gas away from one galaxy and funnel it into the other. It can distort spiral arms into tidal tails, long streamers of stars stretching across hundreds of thousands of light years. It can dump enormous amounts of gas into the center of the merged system, feeding the supermassive black hole lurking there and triggering a quasar, a period where the galactic core outshines every star in the galaxy combined. Mergers don't just rearrange galaxies, they build them. Most of the large galaxies we see today, including our own Milky Way, are the result of repeated collisions and mergers over billions of years. Large galaxies are cannibals. They grow by swallowing smaller galaxies whole. The Milky Way has eaten dozens of smaller galaxies over its lifetime, and it's currently in the process of tearing apart at least two more, the Sagittarius Dwarf Elliptical Galaxy and the Large Magellanic Cloud. In about 4 billion years, the Milky Way will collide with Andromeda, the nearest large spiral galaxy, and the two will merge into a single giant elliptical galaxy that some astronomers have already nicknamed Milkomeda. By the time that merger is complete, the Sun will be a red giant and Earth will be uninhabitable, so we won't be around to see it. But it's going to happen. Galactic collisions are not rare events. They're part of the life cycle. There are two broad types of galaxies that result from this process, and the type you get depends on how the stars inside them move. Spiral galaxies like the Milky Way have a rotating disk of stars, gas and dust, with spiral arms winding outward from a central bulge. The stars in the disk orbit the galactic center in roughly the same plane, like planets orbiting a star. Elliptical galaxies have no disk. Their stars move in random directions, creating a smooth, featureless blob of light with no clear structure. Ellipticals tend to be older, redder, and contain very little gas or dust. Most of their stars formed billions of years ago, and they've been quiet ever since. The question of how you get one versus the other has been debated for decades. One model says that disk galaxies form first. Gas settles into a rotating disk, stars form along spiral arms, and the galaxy stays that way as long as it's left alone. But if two spiral galaxies collide, the merger scrambles the orbits, the disks are destroyed. The stars get flung into random trajectories. The result is an elliptical galaxy, a gravitationally mixed salad with no memory of the orderly disks it used to be. In this model, ellipticals are the end state of galactic evolution, the fossils of ancient collisions. Another factor is the star formation history. If a galaxy forms its stars gradually over billions of years, the gas has time to settle into a disk, and you get a spiral. If the galaxy undergoes a rapid burst of star formation early in its life, converting most of its gas into stars in a short period, the remaining stars settle into a more disordered system, and you get an elliptical. Both processes probably happen. Galaxies are not simple. They don't follow a single script. Some spirals stay spirals for their entire lives. Some ellipticals formed directly from rapid early star formation without ever being spirals. Some galaxies are irregular, with no clear shape at all, often because they've been torn apart by tidal forces from a nearby neighbor. The Milky Way itself is a case study in this process. Current models suggest it started as a dark matter halo that began pulling in gas about 13 billion years ago. Over the next 2 billion years, that gas settled into a rotating disk. Stars formed in the disk, creating the spiral arms we see today. But the Milky Way also has a halo of old stars surrounding the disk, stars that don't follow the neat circular orbits of the disk population. Those halo stars are the remnants of smaller galaxies that merged with the Milky Way early in its history. Each of those mergers added mass, added stars, and left behind a trail of evidence that astronomers are still untangling. The Milky Way's growth pattern is typical. Most large galaxies likely assembled through a combination of steady gas accretion and repeated small mergers, with an occasional large merger reshaping the whole system. Galaxies don't exist in isolation, they cluster. The reason comes back to gravity and the same density fluctuations that seeded galaxy formation in the first place. Regions that were overdense on small scales became galaxies. Regions that were overdense on larger scales became groups and clusters of galaxies. A galaxy group might contain a few dozen galaxies bound together by gravity. A galaxy cluster can contain thousands of galaxies, along with vast amounts of hot gas glowing in X-rays and even more dark matter holding the whole thing together. Clusters themselves group into superclusters, structures hundreds of millions of light-years across. And superclusters are connected by filaments, long thread-like structures of galaxies stretching across the universe like the strands of a cosmic web. Between the filaments are voids, vast regions of space with very few galaxies. Voids can be hundreds of millions of light-years across, nearly empty except for the occasional lonely galaxy drifting through the dark. The cosmic web is the largest structure in the universe. It's the pattern that emerges when you map the positions of millions of galaxies across billions of light-years. It looks organic, like a neural network or the structure of a sponge, with dense nodes connected by thin strands and vast empty spaces in between. That structure is a direct consequence of the initial conditions set by inflation. The pattern you see in the cosmic web today was encoded in the universe when it was a trillionth of a second old. Gravity just took 13 billion years to build it. The discovery of the cosmic web was gradual. In the early 20th century, astronomers thought galaxies were scattered more or less randomly through space. Then, in the 1970s and 80s, large surveys started mapping the three-dimensional positions of galaxies, and the structure became clear. Galaxies were not random, they were organized. They traced out walls and filaments. They avoided voids. The universe had large-scale structure, and that structure told a story about how matter had clumped together under gravity over billions of years. The first major survey to reveal the cosmic web was the CFA Redshift survey in the 1980s, which mapped the positions of thousands of galaxies and found a structure nicknamed the Great Wall, a sheet of galaxies stretching across 500 million light-years. Since then, larger surveys have found even bigger structures: the Sloan Great Wall, the Hercules Corona Borealis Great Wall, which at 10 billion light-years across is one of the largest structures ever observed. Structures that large push up against the cosmological principle, the assumption that the universe should look roughly the same in all directions at the largest scales. If structures can grow that large, it raises questions about how uniform the universe really is. But the cosmic web is not just a curiosity. It's a map of where the dark matter is. Galaxies trace the filaments because that's where the dark matter is densest. The visible matter, The stars and gas we can see is just a tracer. The real structure is invisible. Most of the mass in the cosmic web is dark matter, with the galaxies and hot gas sitting in the gravitational wells it creates. Simulations of the lambda CDM model, where you start with the initial density fluctuations and let gravity run forward for 13 billion years, produce a cosmic web that looks almost identical to what we observe. That match is one of the strongest pieces of evidence that the model is on the right track, even if we don't know what dark matter actually is. Here's what makes dark matter so frustrating. It's everywhere. It outweighs ordinary matter by a factor of about 5 to 1. It's the dominant source of gravity in the universe. Without it, galaxies wouldn't form, the cosmic web wouldn't exist. And yet we have never directly detected a single particle of it. Every experiment designed to find dark matter has come up empty. We know it's there because we can see its gravitational effects. We can measure how fast stars orbit in galaxies. We can watch how light bends around galaxy clusters, a process called gravitational lensing, where the cluster's gravity warps space so much that it acts like a lens, magnifying and distorting the images of more distant galaxies behind it. We can measure the temperature of the hot gas in galaxy clusters and calculate how much mass is needed to hold that gas in place. Every method points to the same conclusion. There's more mass than we can see, a lot more. The leading candidates for what dark matter might be are WIMPs, weakly interacting massive particles, hypothetical particles that interact only through gravity and possibly the weak nuclear force. WIMPs would have been produced in the early universe, and if they exist, they're passing through you right now by the billions without leaving a trace. Detectors buried deep underground in mines and mountains have been searching for WIMPs for decades, waiting for the incredibly rare event where a WIMP collides with an atomic nucleus and leaves a signal. So far, nothing. Other candidates include axions, much lighter particles that were proposed to solve a different problem in particle physics and might also account for dark matter. Or primordial black holes that formed in the first fraction of a second after the Big Bang and have been drifting through space ever since. Or something else entirely that no one has thought of yet. The point is, we don't know. Dark matter is a placeholder. A name for the missing mass we know has to be there because the math doesn't work without it. And the fact that the universe can build galaxies, clusters, and the cosmic web using something we can't see and don't understand is both remarkable and unsettling. It means the universe we observe, the stars and planets and galaxies we can actually see, is a small minority of what's actually out there. Most of the universe is invisible, most of the matter is dark, and the structures we call galaxies are really just the visible tips of enormous dark matter halos, icebergs, where only the smallest part breaks the surface. One of the surprising things Webb has found in the early universe is that galaxies formed faster than the models predicted. Some of the galaxies Webb has observed existed only 500 to 700 million years after the Big Bang, and they're more massive than they should be. In the lambda CDM model, galaxies are supposed to build up slowly, growing through steady accretion and small mergers over billions of years. But the early galaxies Webb is finding look like they assembled too quickly, converting gas into stars at a rate that approaches 100% efficiency. In a normal galaxy, only about 10% of the available gas ever turns into stars. The rest gets blown out by supernovae, or heated too much to collapse, or just drifts away. The early galaxies Webb is seeing seem to have skipped the inefficiency. They turned nearly all their gas into stars in a short burst, which shouldn't be possible under the standard model. Either the model is missing something, or those early galaxies were special in ways we don't yet understand. Galaxy formation is not over. It's still happening. The youngest known galaxy, identified by NASA, formed only about 500 million years ago, meaning it's one of the most recent additions to the cosmic census. Galaxies are still merging. Stars are still forming. The universe is still building structure. In the local universe, galaxy mergers are less common than they were in the early universe, but they still happen. The rate of star formation has been declining for the past 10 billion years. The universe made most of its stars between 8 and 11 billion years ago, during a period called cosmic noon, when the star formation rate peaked. Since then, the rate has been dropping. Galaxies are running out of gas. The raw material for new stars is being used up, and the universe is not making more hydrogen. What we have now is what we'll have for the rest of time. The stars still forming today are using the leftovers, the cosmic web, the clusters, the filaments, the voids. All of it is still evolving. Galaxy clusters are still growing as more galaxies fall into them. Filaments are still funneling gas from the voids into the denser regions, but the overall structure has been set for billions of years. The pattern was laid down early, in the first few 100 million years after the Big Bang, and gravity has been filling in the details ever since. The universe today looks the way it does because of decisions made when it was less than a second old. The quantum fluctuations that inflation stretched to cosmic scales determined where the filaments would grow, where the voids would open up, where galaxies would cluster. The rest was just time. Galaxies are not static objects, they're ecosystems. Gas flows in, stars form, stars die, supernova explosions blow gas back out into space, and the cycle repeats. In spiral galaxies like the Milky Way, the cycle is still running. New stars are forming in the spiral arms at a rate of about 1 to 2 solar masses per year. In elliptical galaxies, the cycle has mostly stopped. The gas is gone. The stars are old. The galaxy is settling into a slow fade, gradually dimming as its stars age and die. Mergers can restart the cycle by dumping fresh gas into a galaxy, triggering a new burst of star formation. But eventually, every galaxy will run out of fuel. The universe will stop making stars. And the galaxies that remain will be filled with the slowly cooling remnants of stars that burned billions of years ago. But that's a problem for the far future. Right now, in this era, galaxies are still alive, still forming stars, still building planets around those stars. And on at least one of those planets, orbiting an unremarkable yellow star in the outer arm of a spiral galaxy, something extraordinary happened. The raw materials scattered into space by dying stars, the carbon and oxygen and nitrogen forged in supernova explosions, came together in just the right way. Molecules formed, chemistry happened, and over billions of years, that chemistry became complex enough to look back at the universe and ask how it got here. The universe had figured out how to make galaxies. It had figured out how to weave them into clusters, filaments, and the cosmic web. And now, inside those galaxies, something even more remarkable was starting to happen. The gas clouds drifting through the spiral arms and the dense cores of young galaxies were doing what gas clouds do when left alone with gravity for long enough. They were collapsing. And when they collapsed, they ignited. Stars were being born. Not the first stars, not the massive population 3 giants that ended the Dark Ages. These were the next generation. Smaller, cooler, longer-lived stars fueled by gas that had been enriched with heavy elements from the supernovae of earlier generations. Stars like the one we orbit today. And around those stars, something unexpected was happening. Planets. A star does not begin its life as a star. It begins as a cloud, a molecular cloud, to be specific, a vast region of space filled with gas and dust, mostly hydrogen, with traces of helium and heavier elements mixed in. These clouds can be enormous, hundreds of light years across, containing enough mass to build thousands or even millions of stars, but they're spread thin. The density inside a molecular cloud is lower than the best vacuum we can create in a laboratory on Earth. You could pass through one and not notice, except for one thing. They're cold, very cold. Temperatures sit at about 10 to 20 degrees above absolute zero. And at those temperatures, atoms move slowly. They can stick together. Dust grains form. Molecules form. The cloud becomes opaque, blocking out starlight from outside. Deep inside these clouds, in the densest regions, gravity is always working. If a pocket of gas happens to be slightly denser than its surroundings, gravity pulls more gas toward it. The pocket grows denser. Gravity gets stronger. More gas falls in. The process accelerates. Eventually, the collapsing pocket of gas becomes so dense and so hot at its center that it starts to glow. Not with nuclear fusion, not yet, but with the heat generated by gravitational compression. This is a protostar, a baby star, still gathering mass, still buried inside the cloud that formed it. Around the protostar, the infalling gas doesn't fall straight in. It has angular momentum, a slight rotation inherited from the turbulence of the original cloud. As the gas spirals inward, conservation of angular momentum forces it to flatten into a disk, the same way a lump of pizza dough flattens when you spin it. This disk is called a protoplanetary disk, and it is where planets are born. The disk contains everything the collapsing cloud had: gas, mostly hydrogen and helium; dust, tiny grains of silicates, carbon compounds, water ice; metals, in the astronomical sense of the word, which means anything heavier than helium; iron, magnesium, oxygen, carbon, nitrogen, all of it swirling in a thin pancake around the newborn star. At the center, the protostar keeps growing. Gas from the disk falls onto it, adding mass, raising the temperature at the core. The protostar fights back. The heat and pressure inside it generate radiation and powerful stellar winds that push outward, slowing the infall. For a while, the system is in balance, gas falling in, radiation pushing out. Then, if the protostar has gathered enough mass, something critical happens. The core reaches about 10 million degrees Kelvin. At that temperature, protons moving fast enough to overcome their mutual electrical repulsion can collide and fuse. Hydrogen fusion ignites. The protostar becomes a star. The energy released by fusion generates enough outward pressure to halt the gravitational collapse. The star settles into a stable phase called the main sequence, where it will spend most of its life steadily converting hydrogen into helium in its core. Our Sun reached this point about 4.6 billion years ago. It formed inside a molecular cloud somewhere in the outer regions of the Milky Way, part of a cluster of newborn stars all igniting around the same time. Most of those sibling stars have since drifted away, scattered by the gravitational interactions of the galaxy. We don't know where they are now. They could be anywhere. But when the Sun first ignited, it was surrounded by a protoplanetary disk, and inside that disk, planets were already starting to form. The process begins with dust. Dust grains in the disk are tiny, about a micrometer across, roughly the size of particles in cigarette smoke. They drift through the gas, occasionally bumping into each other. When they collide, they stick, not through gravity. Dust grains are far too small for gravity to matter at that scale. They stick through electrostatic forces, van der Waals forces, the same weak molecular interactions that let a gecko climb a wall. Grain by grain, the particles grow. A micrometer becomes a millimeter becomes a centimeter becomes a meter. As the clumps get larger, gravity starts to matter. Larger clumps pull in smaller ones. The process accelerates. Within a few 100,000 years, the disk contains billions of these growing clumps, ranging in size from pebbles to boulders to objects the size of asteroids. These are planetesimals, the building blocks of planets. They collide and merge, or they shatter and scatter, depending on the speed of the impact. Slow collisions lead to growth. Fast collisions lead to destruction. The result is a chaotic mess of objects smashing into each other, with the largest ones gradually sweeping up everything in their orbital path. In the inner regions of the disk, close to the star where temperatures are high, only materials that can withstand the heat survive. Rock, metal, silicates. Volatile compounds like water, methane, and ammonia are vaporized by the star's radiation and blown outward by the stellar wind. This is where rocky planets form. Small, dense worlds made of the leftover heavy elements from earlier generations of stars. In our solar system, Mercury, Venus, Earth, and Mars formed in this region. They're all relatively small because there simply wasn't that much rocky material available. Most of the disk's mass was hydrogen and helium, and those elements couldn't condense into solids this close to the Sun. Farther out, beyond a boundary called the frost line, temperatures drop low enough for water to freeze. Suddenly, the amount of solid material available skyrockets. Ice is abundant in protoplanetary disks, far more abundant than rock or metal. The planetesimals forming beyond the frost line had access to a much larger reservoir of building material. They grew faster, accumulating more mass, and once they reached a critical size, something remarkable happened. Their gravity became strong enough to start pulling in the surrounding gas. Hydrogen and helium, the most abundant elements in the disk, began to fall onto these growing cores. The cores became gas giants. Jupiter and Saturn formed this way in our solar system, massive planets with small rocky cores buried under thousands of kilometers of hydrogen and helium. The formation of gas giants has consequences. A planet the size of Jupiter generates a gravitational field strong enough to perturb the orbits of everything nearby. Planetesimals get flung inward toward the star, or outward into the far reaches of the disk. Smaller planets trying to form in neighboring orbits get disrupted. Gas giants act as gravitational vacuum cleaners, clearing out entire regions of the disk and reshaping the architecture of the planetary system. Jupiter's influence is why the asteroid belt between Mars and Jupiter never formed a planet. The material was there, but Jupiter's gravity kept stirring it up, preventing the planetesimals from merging into a single large body. Planet formation is not a calm process. It's violent. Collisions between planetesimals release enormous amounts of energy. Large impacts can melt entire worlds, vaporize atmospheres, shatter moons. Earth itself was struck by a Mars-sized object about 4.5 billion years ago, roughly 100 million years after the solar system formed. The collision vaporized part of Earth's mantle, sent debris into orbit, and formed the Moon from the wreckage. The impact was so violent that it likely melted the entire surface of the planet, turning Earth into a molten ball of rock for millions of years afterward. The Moon we see today is the scar from that collision, a permanent reminder that planet formation is a demolition derby. By the time the chaos settled, about 10 million to 100 million years after the Sun ignited, the basic structure of the solar system was set: 4 rocky planets in the inner system, 4 gas and ice giants in the outer system. countless smaller bodies, asteroids, comets, and dwarf planets scattered throughout. The leftover gas in the disk, the hydrogen and helium that didn't get incorporated into planets, was blown away by the sun's strengthening stellar wind and radiation pressure. What remained was a stable planetary system ready to evolve for billions of years. This process is not unique to our solar system. Protoplanetary disks have been observed around thousands of young stars in nearby stellar nurseries. The Hubble Space Telescope and now the James Webb Space Telescope have imaged these disks in stunning detail, showing spiral arms, gaps, and rings carved out by forming planets. Some disks show asymmetries, clumps of material that might be planets in the process of growing. The existence of these disks confirms that planet formation is a natural byproduct of star formation. Wherever there's a star, there's likely a disk, and wherever there's a disk, there's a chance for planets. But not all stars are the same. The mass of a star determines its life cycle, and that life cycle determines what happens to any planets orbiting it. Massive stars, those weighing more than about 8 times the mass of the Sun, burn through their fuel quickly. They live fast, die young, and end their lives in supernova explosions that obliterate everything nearby. Any planets that formed around a massive star would be vaporized when the star exploded. Low-mass stars, those weighing less than about half the mass of the Sun, burn their fuel slowly. They can live for tens or even hundreds of billions of years, far longer than the current age of the universe. Planets orbiting low-mass stars have stability, but they face other challenges. Low-mass stars are dim, so their habitable zones, the regions where liquid water can exist on a planet's surface, are very close to the star. And at those distances, planets are likely to become tidally locked, with one side permanently facing the star and the other side in eternal darkness. Stars like the Sun, with masses between about half and twice the solar mass, occupy a sweet spot. They live long enough for complex chemistry to develop on their planets. Their habitable zones are at distances where planets aren't tidally locked. They're stable enough not to flare violently and strip away planetary atmospheres, and they're common enough that the galaxy contains billions of them. If you're looking for a star that could host life, a Sun-like star is a good bet. The Sun will spend about 10 billion years on the main sequence, steadily fusing hydrogen into helium in its core. It's currently about halfway through that phase. In another 5 billion years, the hydrogen in the core will run out. The core will contract and heat up, and the outer layers will expand. The Sun will become a red giant, swelling to roughly the orbit of Earth. Mercury and Venus will be engulfed. Earth might survive, though it will be scorched to a lifeless cinder. Eventually, the Sun will shed its outer layers in a series of pulses, creating a planetary nebula, a glowing shell of gas expanding into space. What's left of the core will cool and contract into a white dwarf, a dense, Earth-sized remnant that will glow faintly for trillions of years before fading completely. But that's the far future. Right now, the Sun is stable, and on the third planet from the Sun, something extraordinary happened. Life. Earth is not the only rocky planet in the solar system. It's not even the only planet in the habitable zone. Mars also sits in the habitable zone, at least on the outer edge. Venus might have been habitable early in its history before a runaway greenhouse effect turned it into a hellscape with surface temperatures hot enough to melt lead. But Earth is the only planet we know of that developed life. The question is why? What makes Earth special? The answer is a combination of factors, some of them obvious, some of them subtle, and some of them still debated. First, Earth is the right size. If a planet is too small, it can't hold on to its atmosphere. Gases in the atmosphere move faster at higher temperatures, and if a planet's gravity is too weak, those gases escape into space. Mars is smaller than Earth, and it lost most of its atmosphere billions of years ago. The solar wind stripped it away once Mars's magnetic field shut down. Earth, being larger, has stronger gravity and has managed to hold on to its atmosphere for 4.5 billion years. Second, Earth has liquid water, a lot of it. Roughly 70% of Earth's surface is covered by oceans. Water is critical for life as we understand it. It's a solvent, meaning other molecules can dissolve in it and react. It stays liquid over a wide range of temperatures. It's chemically stable. It's abundant in the universe. Without liquid water, the chemistry that leads to life as we know it doesn't happen. Earth sits at the right distance from the sun, not too hot, not too cold, for water to remain liquid on the surface. That region is called the habitable zone, and Earth is comfortably inside it. Third, Earth has a magnetic field. The planet's core is made of molten iron, and the motion of that iron generates a magnetic field that extends far into space. That field acts as a shield, deflecting charged particles from the solar wind that would otherwise strip away the atmosphere. Mars lost its magnetic field early in its history, and as a result, it lost its atmosphere. Earth's magnetic field has protected its atmosphere for billions of years, maintaining the conditions needed for liquid water and life. Fourth, Earth has plate tectonics. The surface of the planet is broken into large plates that move over geological timescales. Plates collide, creating mountains. Plates pull apart, creating ocean basins. Volcanic activity releases gases from the interior, replenishing the atmosphere. Plate tectonics acts as a thermostat, regulating the planet's climate by cycling carbon dioxide between the atmosphere, the oceans, and the rocks. Without plate tectonics, Earth's climate would have drifted out of the habitable range billions of years ago. Fifth, Earth has a moon, and not just any moon, a large moon, roughly a quarter the size of Earth, unusually large for a planet this size. The moon stabilizes Earth's axial tilt, preventing wild swings in climate that would make long-term habitability difficult. The moon also drives tides, which may have played a role in the evolution of early life by creating tidal pools where organic molecules could concentrate and react. And sixth, Earth is made of the right stuff. The heavy elements that make up Earth, carbon, oxygen, nitrogen, phosphorus, sulfur, iron, all of them were forged inside stars that died before the solar system formed. When those stars exploded as supernovae, they scattered those elements into space. The molecular cloud that collapsed to form the sun and planets was seeded with the products of stellar nucleosynthesis. Without supernovae, there would be no rocky planets. Without rocky planets, there would be no life. Every atom in your body heavier than hydrogen was made inside a star that died billions of years ago. You are stardust, assembled into a configuration complex enough to contemplate its own origins. That's not a metaphor. That's chemistry. Life on Earth appeared quickly, at least by geological standards. The planet formed about 4.6 billion years ago. For the first few 100 million years, it was a molten hellscape, bombarded by asteroids and comets left over from the planet formation process. The late heavy bombardment, a period of intense impacts that ended about 3.8 billion years ago, likely sterilized the surface multiple times. But by 3.5 billion years ago, there is clear evidence of life in the form of fossilized microbial mats called stromatolites. Life appeared almost as soon as conditions allowed it. That suggests life might not be rare. It might be an inevitable outcome of the right chemistry in the right environment, but life on Earth stayed simple for a very long time. For more than 2 billion years, life was nothing but single-celled organisms, bacteria and archaea floating in the oceans, metabolizing whatever chemicals they could find. It wasn't until about 2 billion years ago that more complex cells, eukaryotes, appeared. And it took another billion years for multicellular life to emerge. The Cambrian explosion, the sudden diversification of complex life forms, happened only 540 million years ago. Humans, modern Homo sapiens, have been around for less than 300,000 years. On a timeline where Earth is 4.6 billion years old, humans showed up in the last second of the last minute of the last hour of the last day. The conditions that allowed life to emerge and evolve on Earth are specific, but they're not unique. The ingredients are common. Water is abundant. Carbon is abundant. Nitrogen, oxygen, phosphorus, all common products of stellar nucleosynthesis. Rocky planets, inhabitable zones, exist around many stars. The question is not whether the conditions for life exist elsewhere. They almost certainly do. The question is whether life actually arose, and if it did, whether it survived long enough to become complex. Those are harder questions to answer. Looking out at the galaxy, at the hundreds of billions of stars, at the trillions of planets those stars likely host, it seems implausible that Earth is the only place where life took hold. But we don't know. We've looked, we've listened, we've sent probes to Mars and Europa and Titan. We've scanned the skies for radio signals from other civilizations. So far, nothing. The silence is deafening. It's possible life is common, but intelligence is rare. It's possible intelligent life tends to destroy itself before it becomes detectable. It's possible we're looking in the wrong places or listening at the wrong frequencies, or it's possible we're alone. That possibility is just as scientifically valid as any other, and it's the one possibility that most people find hardest to accept. But whether or not life exists elsewhere, the fact remains that it exists here, and the chain of events that led to it is staggering. Quantum fluctuations during inflation seeded the density variations that became galaxies. Galaxies formed stars. Stars fused hydrogen into heavier elements. Stars died and scattered those elements into space. New stars formed from the enriched gas. Protoplanetary disks formed around those stars. Dust grains stuck together. Planetesimals grew. Planets formed. One of those planets, orbiting an unremarkable yellow star in the outer arm of a spiral galaxy, ended up with the right combination of size, composition, distance, magnetic field, moon, and geological activity to remain habitable for billions of years. And on that planet, chemistry became biology. Molecules became cells. Cells became organisms. Organisms became complex. And eventually, one of those organisms looked up at the night sky and started asking questions. But life is fragile. Stars die. Planets cool. Magnetic fields weaken. Atmospheres erode. And in the hearts of galaxies, in the dense cores where millions of stars orbit in crowded chaos, there are objects so massive, so dense, so gravitationally powerful that even light cannot escape them. Objects that warp space and time, that devour stars, that anchor galaxies and occasionally tear them apart. Objects that challenge everything we thought we understood about matter, energy, and the limits of physics. They're called black holes, and they're not empty, they're not holes, they're the opposite. They're the most concentrated mass in the universe, packed into the smallest possible space. And understanding them requires breaking almost every rule you've ever been taught about how the universe works. The universe had figured out how to make life. It had assembled stars, planets, oceans, and the chemistry that eventually looked up at the sky and started asking questions. But standing between those questions and their answers, lurking in the centers of galaxies and scattered throughout the cosmos, are objects so extreme, so fundamentally strange, that even naming them feels inadequate. We call them black holes, which makes them sound like empty spaces, voids, absences. They are the opposite. They are the most concentrated mass in the universe, gravity taken to its logical conclusion, matter compressed to densities so extreme that the rules of physics you learnt in school stop applying. And they are everywhere. There are millions of them in our galaxy alone. Tens of millions of supermassive ones sitting in the cores of galaxies across the observable universe. And until very recently, we had never actually seen one. A black hole is what happens when you take a lot of mass and compress it into a very small space. How much mass? How small a space? The answers depend on the type of black hole, but the principle is the same. Pack enough matter into a tight enough region, and the gravitational pull becomes so strong that nothing, not even light, can escape. The boundary where escape becomes impossible is called the event horizon, and it is the defining feature of a black hole. Cross that line and you are gone. Not gone in the sense of destroyed, at least not immediately. Gone in the sense that you have left the universe. You are still somewhere, presumably, but that somewhere is causally disconnected from the rest of space-time. Anything you do, any signal you send, any light you emit, none of it will ever reach the outside world. The event horizon is a one-way door, and there is no handle on the inside. Black holes come in different sizes, and the process that creates them depends on the size. The smallest confirmed black holes weigh a few times the mass of the Sun. These are stellar mass black holes, and they form when massive stars die. Not all stars, not even most stars. Only stars that weigh more than about 20 times the mass of the Sun have enough mass to collapse into black holes. Smaller stars end their lives as white dwarfs or neutron stars, dense remnants that avoid total collapse by relying on quantum pressure to hold themselves up. But above a certain mass, no known force in physics can prevent the collapse. When a star massive enough runs out of fuel, the core implodes in a fraction of a second. The outer layers rebound in a supernova explosion, one of the most violent events in the universe, bright enough to outshine entire galaxies for a few weeks. And at the center, where the core used to be, space-time itself folds inward. A black hole is born. The process is fast. Once the collapse begins, it takes less than a second for the core to cross its own event horizon. The infalling matter doesn't stop. It keeps collapsing, shrinking down to a point of infinite density that physicists call a singularity. Except calling it a point is probably wrong, and calling it infinite is definitely a sign that the math has broken. Singularities are where general relativity, Einstein's theory of gravity, stops giving useful answers. The equations return infinity, which in physics is usually a polite way of saying, we don't know what happens here. The singularity is hidden inside the event horizon, shielded from view, and that's probably a good thing. Roger Penrose, a mathematician who won the Nobel Prize for his work on black holes, proved in the 1960s that singularities are unavoidable once a black hole forms. They are not artifacts of the math, they are real features of space-time, at least according to general relativity. Whether quantum mechanics changes that picture is still an open question. Stellar mass black holes are common. Our galaxy probably contains tens of millions of them, the leftover corpses of massive stars that died over the past 13 billion years. Most of them are invisible, drifting through space in the dark. We only detect them when they interact with something else. If a black hole happens to be in a binary system with a normal star, it can pull gas off the star's surface. That gas spirals inward, forming an accretion disk, a swirling pancake of doomed matter heating up from friction as it falls toward the event horizon. The disk gets hot, very hot. Hot enough to glow in X-rays. And we can see X-rays. By mapping X-ray sources in the sky, astronomers have identified dozens of stellar mass black holes in our galaxy, all of them betrayed by the light from the matter they're consuming. Then there are the monsters, supermassive black holes. These sit at the centers of galaxies, including our own, and they weigh millions or even billions of times the mass of the Sun. The black hole at the center of the Milky Way is called Sagittarius A star, and it weighs about 4 million solar masses. That sounds enormous, and it is, but it's actually on the small side for a supermassive black hole. The black hole at the center of the galaxy M87 weighs about 6.5 billion solar masses. The one at the center of the quasar Tone 618 weighs roughly 66 billion solar masses, making it one of the largest black holes ever confirmed. These objects are not just big, they are so massive that their event horizons stretch for billions of kilometers. Light would take hours or even days to cross from one side to the other. If you replaced the Sun with Sagittarius A star, the event horizon would extend past the orbit of Mercury. If you replaced it with the black hole in M87, the event horizon would reach beyond the orbit of Neptune. How did they get so big? That is one of the most debated questions in astrophysics. Stellar mass black holes form from the deaths of massive stars. That process is well understood. But supermassive black holes are too heavy to have formed that way. Even if you started with a stellar mass black hole and fed it constantly at the fastest rate physics allows, you couldn't grow a billion solar mass black hole in the age of the universe. The math doesn't work. So either supermassive black holes formed through a different process, or they started with much larger seeds. One idea is direct collapse. In the early universe, under specific conditions, a giant cloud of gas could have skipped the star formation process entirely and collapsed straight into a black hole weighing 100,000 solar masses or more. Starting with a seed that large gives you a massive head start. Another idea is runaway mergers. In the dense cores of the first galaxies, stellar mass black holes could have collided and merged repeatedly, rapidly building up mass. A third idea is primordial black holes that formed in the first fraction of a second after the Big Bang, seeded by density fluctuations in the earliest moments of the universe. If they existed, they would have been growing for 13.8 billion years, and that's enough time to reach the masses we observe. We don't know which answer is right. We might never know. What we do know is that supermassive black holes were already in place early in the universe's history. The James Webb Space Telescope has found quasars powered by supermassive black holes that existed less than 1 billion years after the Big Bang. That's not enough time to grow them the slow way, which means the early universe was doing something we still don't fully understand. Either black hole formation was much faster in the early universe, or the seeds were much larger, or both. Supermassive black holes don't just sit quietly at the centers of galaxies, they feed. Gas and stars wander too close, and gravity pulls them in. The infalling matter doesn't fall straight down. It has angular momentum, so it spirals inward, forming an accretion disk. The disk heats up from friction and from the tidal forces generated by the black hole's gravity. Temperatures in the inner regions of the disk can reach millions of degrees. At those temperatures, the disk glows, not in visible light, in ultraviolet and X-rays. The radiation from the disk is so intense it can outshine every star in the galaxy combined. When that happens, the galaxy's core becomes what astronomers call an active galactic nucleus, or AGN. If the black hole is feeding particularly aggressively, the core becomes a quasar, one of the brightest objects in the universe. Quasars were discovered in the early 1960s, though no one knew what they were at first. They looked like faint blue stars in photographs, but their spectra were bizarre, showing emission lines that didn't match any known element. It took years to realize the lines were normal hydrogen and helium lines, just redshifted by enormous amounts. The objects weren't nearby stars. They were the cores of extremely distant galaxies, seen as they existed billions of years ago when the universe was young, and they were absurdly bright. A single quasar can emit more light than 1 trillion suns. The only way to generate that much energy in such a small region is a supermassive black hole feeding on an enormous supply of gas. The energy released by accretion onto a supermassive black hole doesn't just light up the sky, it affects the entire galaxy. The radiation from the accretion disk heats the surrounding gas, preventing it from cooling and collapsing to form new stars. Jets of particles, accelerated to nearly the speed of light by magnetic fields near the black hole, shoot outward from the poles of the disk, punching through the galaxy and blasting gas into intergalactic space. This process is called feedback, and it's one of the main ways supermassive black holes regulate star formation in galaxies. Without feedback, galaxies would convert all their gas into stars much faster than they actually do. The black hole acts as a thermostat, keeping the galaxy from overheating by shutting down star formation when the gas supply gets too concentrated near the center. This is not speculation. Observations show a tight correlation between the mass of a galaxy's central black hole and the mass of its bulge, the dense spherical region of old stars at the galaxy's core. The black hole typically weighs about 1/1000th the mass of the bulge. That ratio holds across galaxies of all sizes, from small galaxies with black holes weighing a few million solar masses to giant ellipticals with black holes weighing tens of billions. The correlation is so tight it suggests the black hole and the galaxy grew together, influencing each other's evolution. The black hole fed on gas funneled toward the center by galaxy mergers or gravitational instabilities. As it fed, it released energy that heated the surrounding gas and slowed the infall. The balance between infall and feedback determined how large both the black hole and the galaxy could grow. For decades, black holes were theoretical objects, predicted by general relativity, supported by indirect evidence, but never directly observed. We saw the effects of black holes: X-ray binaries, quasars, stars orbiting invisible companions, but we never saw the event horizon. That changed in 2019 when the Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, released the first direct image of a black hole. The target was the supermassive black hole at the center of M87, and the image showed exactly what theory predicted: a dark, circular region, the shadow of the event horizon, surrounded by a bright ring of glowing gas in the accretion disk. The ring was asymmetric, brighter on one side because the gas on that side was moving toward us at relativistic speeds, and its light was Doppler boosted. The image wasn't just a picture, it was a test of general relativity in the most extreme conditions we've ever observed, and general relativity passed. 2 years later, the Event Horizon Telescope released an image of Sagittarius A star, the black hole at the center of our own galaxy. This one was harder. Sagittarius A star is much smaller than the black hole in M87, and the gas around it churns and changes on timescales of minutes. The team had to combine data from multiple nights of observations and use sophisticated algorithms to extract a stable image from the chaos. But the result was the same: a dark shadow surrounded by a bright ring. The black hole at the center of the Milky Way, invisible for the entire history of human civilization, had finally been photographed. Black holes also reveal themselves through gravitational waves, ripples in spacetime produced by accelerating masses. Einstein predicted gravitational waves in 1916, but he thought they would be too weak to detect. He was almost right. Detecting them required building the most sensitive instruments ever constructed: laser interferometers with arms several kilometers long, capable of measuring distance changes smaller than the width of a proton. The Laser Interferometer Gravitational Wave Observatory, LIGO, came online in the early 2000s and spent years listening to the universe, hearing nothing. Then, on September 14, 2015, both LIGO detectors, one in Louisiana and one in Washington state, recorded the same signal within milliseconds of each other. The signal lasted less than a second, a rising chirp that swept upward in frequency and amplitude before cutting off abruptly. It was the gravitational wave signature of two black holes, weighing about 30 solar masses each, spiraling together and merging into a single larger black hole. The detection was announced in February 2016, and it changed everything. Gravitational waves are not light. They don't get absorbed by dust or scattered by gas. They travel through the universe unimpeded, carrying information about events that are completely invisible to telescopes. The merger LIGO detected happened more than 1 billion light-years away, in a region of space with no visible counterpart. Without gravitational waves, we would never have known it happened. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, along with neutron star mergers, and a handful of hybrid events involving one black hole and one neutron star. Each detection is a window into the universe's violent side, a reminder that space is not calm. It's full of objects smashing into each other, releasing energy in bursts that dwarf anything we can produce on Earth. Gravitational wave astronomy is still in its infancy. LIGO's sensitivity is improving with each upgrade. New detectors are being built in Japan and India. A space-based detector called LISA, the Laser Interferometer Space Antenna, is planned for the 2030s. LISA will be sensitive to lower-frequency gravitational waves, the kind produced by supermassive black hole mergers. When two galaxies collide, their central black holes spiral together over millions of years, eventually merging in a burst of gravitational waves that LISA should be able to detect from across the observable universe. The first detection of a supermassive black hole merger will be one of the landmark events in astronomy, a direct observation of the process that shaped the largest structures in the cosmos. Black holes are not eternal. This is one of the strangest predictions of theoretical physics. Stephen Hawking showed in the 1970s that black holes emit radiation, a quantum effect where particle-antiparticle pairs pop into existence near the event horizon, and one particle falls in while the other escapes. The escaping particle carries energy away from the black hole, which means the black hole loses mass. The process is called Hawking radiation, and it's incredibly slow for large black holes. A black hole, the mass of the Sun, would take 10 to the 67th years to evaporate, far longer than the current age of the universe. A supermassive black hole would take even longer. But eventually, given enough time, every black hole in the universe will radiate away its mass and disappear in a final burst of energy. The universe will be left with nothing but faint remnants of radiation, the last whispers of objects that once dominated the cosmos. but that's trillions upon trillions of years in the future. Right now, black holes are very much alive. They anchor galaxies, they regulate star formation, they produce the brightest objects in the universe. They warp space-time into shapes so extreme that time itself slows near the event horizon. If you could hover just outside the event horizon of a supermassive black hole, which you couldn't because the tidal forces would tear you apart, you would see the universe outside sped up. Stars would age in seconds, galaxies would collide in minutes. Billions of years of cosmic history would flash by while you experienced only moments. Time is not a universal constant near a black hole. It's relative, flexible, dependent on where you are and how strong the gravity is. Einstein predicted this in 1915. A century later, we've confirmed it by watching stars orbit Sagittarius A star and measuring how their light redshifts as they climb out of the black hole's gravitational well. Black holes are not villains. They're not cosmic vacuum cleaners sucking up everything nearby. They're gravitational anchors, no different from any other mass except that they're incredibly dense. If you replaced the Sun with a black hole of the same mass right now, Earth's orbit wouldn't change. We'd freeze in the dark, yes, but gravitationally nothing would move. You only get pulled into a black hole if you get too close, and too close for a stellar mass black hole is only a few kilometers. For Sagittarius A star, it's millions of kilometers. The galaxy is not in danger of falling in. The stars near the galactic center are orbiting the black hole at safe distances, the way planets orbit the Sun. Some of those stars pass within a few light hours of the event horizon, moving at a measurable fraction of the speed of light, and they survive the experience. Black holes are dangerous, but they're not magic. They follow the same gravitational rules as everything else. They're just very, very concentrated. And they are not the strangest thing in the universe. That distinction belongs to something even more invisible, even more mysterious, something that doesn't glow, doesn't collapse, doesn't interact with light or ordinary matter at all, except through gravity. Something that makes up most of the matter in the universe, and yet has never been directly detected. Something without which galaxies wouldn't exist, stars wouldn't form, and we wouldn't be here asking questions. Black holes, at least, are made of normal matter that collapsed. What comes next is something else entirely. Something that was there from the beginning, shaping the universe in ways we're only now starting to understand. Something invisible, holding the cosmos together, paired with something even stranger pushing it apart. The unseen architects, dark matter and dark energy. And they're not optional details, they're the foundation. Without them, nothing you've read so far would have been possible. The universe had figured out how to make black holes, objects so dense, so gravitationally extreme that they could anchor entire galaxies, regulate star formation, and bend space-time into shapes that made clocks run slow and light bend into rings. Black holes were made of normal matter, at least at first. Stars that collapsed, gas that fell in, ordinary stuff compressed to extraordinary densities. We could see the effects. We could photograph the event horizons. We could detect the gravitational waves when two of them merged. Black holes were strange, yes, but they were comprehensible. They followed the rules of general relativity. They were predictable. And then there's the rest of the universe, the part we can't see. The part that doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter except through gravity. The part that makes up most of the mass in the cosmos and yet has never been directly detected by any instrument we've ever built. Dark matter. And its even stranger companion, dark energy, a force that doesn't pull things together like gravity does. It pushes them apart, and it's winning. Together, dark matter and dark energy make up roughly 95% of the universe. Everything you can see, every star, every planet, every galaxy, every atom in your body, all of it is ordinary matter, and ordinary matter accounts for about 5% of the total. 5%. The universe we experience, the one we measure and photograph and write equations about, is a rounding error. The rest is invisible, and it's not hiding in some distant corner of the cosmos. It's everywhere. It's in this room. It's passing through you right now. And we only know it exists because without it, nothing we see would make sense. Let's start with dark matter, because the evidence for it is older and more direct. The story begins in the 1930s with an astronomer named Fritz Zwicky, a Swiss physicist working at Caltech who had a reputation for being brilliant, abrasive, and utterly uninterested in making friends. Zwicky was studying the Coma cluster, a massive grouping of galaxies about 300 million light-years away. He measured how fast the galaxies in the cluster were moving, and he used those velocities to calculate how much mass the cluster must contain to hold itself together. The galaxies were moving fast, too fast. According to his calculations, they should have been flying apart. The gravity from all the visible stars and gas in the cluster wasn't nearly enough to keep them bound. There had to be more mass, a lot more. Mass that wasn't glowing, mass that wasn't visible in any telescope. Zwicky called it dark matter. Nobody believed him. The measurements were difficult, the conclusions were strange, and Zwicky had a habit of insulting anyone who disagreed with him. His idea was ignored for decades. Then, in the 1970s, an astronomer named Vera Rubin started measuring the rotation curves of spiral galaxies. The rotation curve shows how fast stars and gas are orbiting at different distances from the galactic center. In a solar system, planets farther from the Sun orbit more slowly because the Sun's gravity weakens with distance. You'd expect the same thing in a galaxy. Stars near the center should orbit quickly because most of the galaxy's mass is concentrated there. Stars farther out should orbit more slowly. That's what Newton's laws predict. That's what every physicist expected to see. Rubin found the opposite. Stars far from the galactic center were orbiting just as fast as stars near the center. The rotation curves stayed flat. They didn't drop off the way they should. The only way to explain that was to assume the galaxy contained far more mass than anyone could see. And that mass couldn't be concentrated at the center. It had to be spread out in a vast halo surrounding the visible galaxy, extending far beyond the edge of the starlight. A halo of invisible matter holding the galaxy together, dark matter. Rubin's measurements were meticulous. She observed dozens of galaxies. They all showed the same pattern: flat rotation curves, too much gravity, invisible mass. The conclusion was unavoidable. Galaxies were embedded in dark matter halos, and those halos outweighed the visible matter by a factor of 5 or 6 to 1. For every star you could see, there were 5 stars worth of mass you couldn't see, and whatever that mass was made of, it wasn't stars. It wasn't gas, it wasn't dust, it was something else. The evidence piled up. Gravitational lensing provided another line of proof. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of the cluster bends the light, acting like a lens. The amount of bending depends on the mass of the cluster. When astronomers measured the lensing effect of galaxy clusters, they found the same problem Zwicky had found. The clusters were bending light more than they should based on the visible mass. There was extra mass, invisible mass, dark matter. And by mapping how the light bent, astronomers could create maps of where the dark matter was. The maps showed massive halos surrounding every galaxy, diffuse clouds of invisible stuff extending far beyond the visible edges. The largest structures in the universe, the filaments and clusters of the cosmic web, were held together not by stars but by dark matter. The visible galaxies were just tracers, markers showing where the dark matter had clumped together strongly enough to pull in gas and ignite stars. By the early 2000s, the case for dark matter was airtight. Multiple independent lines of evidence all pointed to the same conclusion. The universe contained roughly 5 times more dark matter than ordinary matter. Cosmologists folded it into the standard model. Lambda CDM, short for lambda cold dark matter, became the framework for understanding how the universe evolved. Lambda represented dark energy, which we'll get to. CDM represented cold dark matter, a hypothetical form of matter that doesn't interact with light, doesn't emit radiation, doesn't collide with itself, and clumps together under gravity without heating up. Cold means the particles are moving slowly, at least compared to the speed of light. Hot dark matter, by contrast, would be made of particles moving at relativistic speeds, and simulations show that hot dark matter doesn't produce the structure we see in the universe. Galaxies would be smeared out, filaments would be fuzzier, clusters would look different. Cold dark matter fits the observations, hot dark matter doesn't. The problem is, we don't know what cold dark matter is, we know what it does. We know how much of it there is, roughly 27% of the total mass energy of the universe. We know it clumps together under gravity. We know it doesn't interact with ordinary matter except gravitationally, but we don't know what particle makes it up. The leading candidate for decades has been WIMPs, weakly interacting massive particles. These are hypothetical particles that interact only through gravity and the weak nuclear force, the same force responsible for radioactive decay. If WIMPs exist, they would have been produced in enormous numbers in the early universe, and they would still be around today, passing through ordinary matter like ghosts. Every second, billions of WIMPs might be streaming through your body without leaving a trace. Detectors built to catch them, massive tanks of ultra-pure materials buried deep underground to shield them from cosmic rays, have been running for decades. They've found nothing, not a single confirmed WIMP detection. That doesn't mean WIMPs don't exist. It means they're either rarer or interact even more weakly than we thought, or they're not WIMPs at all. Other candidates have been proposed. Axions, hypothetical particles much lighter than WIMPs, originally invented to solve a different problem in particle physics. Sterile neutrinos, a heavier cousin of the neutrinos we already know exist. Primordial black holes, tiny black holes that could have formed in the first fraction of a second after the Big Bang. Each idea has its supporters and its problems. None has been confirmed. There's also machos, massive compact halo objects. These are not exotic particles. They're ordinary matter, just in forms that don't shine. Brown dwarfs, failed stars that never ignited fusion, rogue planets drifting through interstellar space, white dwarfs, neutron stars, black holes, objects that have mass but don't emit much light. In the 1990s, astronomers searched for machos by looking for gravitational microlensing, the brief brightening of a distant star when a macho passes in front of it and bends its light. They found some, not enough. Machos can account for maybe 20% of the dark matter at most. The rest has to be something else, something that's not made of protons, neutrons, or electrons. Something outside the standard model of particle physics, something we've never detected in a lab. The frustrating part is that dark matter was there from the beginning. It dominated the early universe. It was the scaffolding that allowed galaxies to form. Without dark matter, the tiny density fluctuations left over from inflation would have grown too slowly. By the time gravity pulled enough ordinary matter together to form the first stars, the universe would have expanded so much that nothing would have clustered. No galaxies, no stars, no planets, no us. Dark matter collapsed first, creating gravitational wells that ordinary matter fell into. It built the framework. The visible universe just filled in the details. And dark matter is still out there, holding everything together. The Milky Way is embedded in a dark matter halo that extends far beyond the visible stars. That halo weighs about 1 trillion solar masses, 10 times the mass of all the stars in the galaxy combined. Most of the Milky Way's gravity comes from matter we can't see. When you feel the pull of the galaxy's gravity, when you think about the stars orbiting the galactic center, most of what they're orbiting isn't stars, it's the invisible halo. Dark matter is the skeleton, ordinary matter is the skin. Now let's talk about dark energy, because dark energy is stranger. Dark matter at least behaves like matter. It clumps, it pulls things together. It makes sense, even if we don't know what it's made of. Dark energy does the opposite. It pushes, it doesn't clump, it doesn't weaken with distance the way gravity does. And it's everywhere, filling every cubic centimeter of space, driving the universe apart faster and faster. The discovery of dark energy came from supernovae. In the late 1990s, 2 independent teams of astronomers were measuring the distances to Type 1a supernovae, a specific kind of exploding star that has a predictable peak brightness. Because the brightness is known, you can use these supernovae as standard candles to measure how far away their host galaxies are. Combine that distance with the redshift of the galaxy, which tells you how fast it's receding, and you can map the expansion history of the universe. The goal was to measure how much the expansion was slowing down. Everyone expected the universe to be decelerating. Gravity pulls everything together, so the expansion should be slowing over time. The question was how much. The answer was shocking. The universe wasn't slowing down, it was speeding up. Distant supernovae were fainter than they should be, which meant they were farther away than expected. Galaxies that should have been closer, given their redshifts, were actually more distant. Something was pushing them apart, counteracting gravity, accelerating the expansion. The teams announced their results in 1998, and the discovery won the Nobel Prize. It also broke cosmology, because nothing in the standard model predicted this. Gravity pulls, it doesn't push. The universe should be slowing down, not speeding up. The only way to explain the acceleration was to add a new component to the universe, something with negative pressure, something that acts like a repulsive force. Dark energy. Dark energy makes up about 68% of the total energy density of the universe. That's more than twice as much as dark matter. It's the dominant component, and it's growing in importance. As the universe expands, the density of matter drops. Galaxies spread apart, stars drift farther from each other, and the average density of ordinary and dark matter decreases. But dark energy doesn't dilute. It stays constant, or at least nearly constant, as space expands. More space means more dark energy. The total amount of dark energy in the universe is increasing every second, and that means its influence is increasing. Early in the universe's history, when everything was packed tightly together, matter dominated. Gravity was stronger than dark energy. The expansion was slowing. But about 5 billion years ago, the density of matter dropped below a critical threshold. Dark energy took over. The expansion started accelerating, and it's been accelerating ever since. The simplest explanation for dark energy is the cosmological constant, represented by the Greek letter lambda. Einstein introduced the cosmological constant in 1917 as a fudge factor in his equations of general relativity. He was trying to build a model of a static universe, one that neither expanded nor contracted, and he needed something to counteract gravity. The cosmological constant was that something, a constant energy density built into the fabric of space itself. When Edwin Hubble discovered the universe was expanding, Einstein abandoned the cosmological constant, reportedly calling it his biggest blunder. Turns out he was right the first time. The cosmological constant is back, and it fits the data. If space itself has a small intrinsic energy density, a kind of vacuum energy that doesn't change as the universe expands, it produces exactly the kind of accelerated expansion we observe. The problem is, nobody knows why the cosmological constant has the value it does. Quantum field theory predicts a vacuum energy density, but the prediction is off by a factor of 10 to the 120th power. That's not a small error. That's one of the worst predictions in the history of physics. Something is cancelling out most of the vacuum energy, leaving behind a tiny residual that happens to be just the right size to explain dark energy. We don't know what. We don't know why. It's a coincidence so absurd that most physicists refuse to believe it's really a coincidence. The alternative is quintessence, a dynamic form of dark energy that changes over time. Instead of a constant vacuum energy, quintessence is a field, similar to the inflaton field that drove inflation in the first fraction of a second after the Big Bang. The field has energy, and that energy can vary depending on the field's value and how it's rolling through its potential. If quintessence is real, dark energy wasn't always the same strength. It could have been weaker in the past, and it could get stronger in the future, or vice versa. The expansion rate of the universe would change over time in ways that a cosmological constant doesn't allow. Some observations hint at this. Measurements of the Hubble constant, the current expansion rate, show tension between different methods. Direct measurements using nearby supernovae give one answer. Measurements based on the cosmic microwave background give a different answer. The discrepancy is small, but it's persistent, and it's driving cosmologists quietly insane. Quintessence is one possible explanation. If dark energy is changing over time, it could explain the tension, but it could also just be a measurement error. The jury is still out. Dark matter and dark energy are not just mysterious, they're fundamental. They shape the universe at every scale. Dark matter built the galaxies. Without it, the cosmic web wouldn't exist. Stars wouldn't have places to form. Planets wouldn't have places to orbit. Dark energy determines the universe's fate. If dark energy stays constant, the universe will keep expanding faster and faster. Galaxies outside our local group will eventually recede faster than light, not because they're moving through space faster than light, but because the space between us and them is expanding faster than light can cross it. We'll lose sight of them. The observable universe will shrink. In a few 100 billion years, an observer in the Milky Way will see a much emptier sky. Most galaxies will have disappeared beyond the cosmic horizon. Only the local group, the small cluster of galaxies bound together by gravity, will remain visible. The rest of the universe will be gone, unreachable, invisible. If dark energy gets stronger over time, things get worse, much worse. In a scenario called the Big Rip, dark energy eventually becomes so strong it starts tearing apart structures held together by gravity. First galaxy clusters dissolve, then individual galaxies, then solar systems, then planets. Eventually, dark energy gets strong enough to overcome the forces holding atoms together. Molecules are ripped apart, atoms are ripped apart. Even atomic nuclei are torn to pieces. The universe ends not in fire or ice, but in disintegration. Every structure, every bond, every connection, undone by the accelerating expansion of space. The Big Rip is speculative, Most cosmologists don't think dark energy is getting stronger, but it's allowed by the data. We can't rule it out. Then there's the opposite possibility. If dark energy is not a cosmological constant, but a field like quintessence, it could weaken over time, or it could reverse. If dark energy turns negative, it would start pulling instead of pushing. The expansion would slow, stop, and reverse. The universe would start contracting. Galaxies would begin moving toward each other instead of away. The cosmic microwave background would blue shift instead of red shift. Over billions of years, the universe would collapse back into a hot, dense state, a big crunch, the time reverse of the Big Bang. Some models suggest the Big Crunch could bounce, igniting a new Big Bang and starting the cycle over, a cyclic universe, expanding and contracting forever. Elegant, maybe, but entirely speculative. We have no evidence the universe has done this before. We have no evidence it will do it again. What we do know is that dark matter and dark energy are real. They're not placeholders, they're not mistakes. Multiple independent lines of evidence confirm them. Rotation curves, gravitational lensing, the cosmic microwave background, supernova distances, the large-scale structure of the universe, all of it points to the same conclusion. Most of the universe is invisible. Most of it doesn't interact with light. And most of it is pushing the cosmos apart, not pulling it together. The universe we see is a thin film on the surface of something much larger and much stranger. The fact that we can't detect dark matter particles in a lab is frustrating, but it's not fatal. We've never directly detected a neutrino either, at least not until the 1950s, decades after they were predicted. Neutrinos interact so weakly with ordinary matter that trillions of them pass through your body every second without leaving a trace. Detecting them required building massive underground tanks of water and waiting for the incredibly rare event where a neutrino collided with an atom and produced a flash of light. Dark matter might be similar. The experiments are running. The detectors are getting more sensitive. If dark matter is made of particles, we'll find them eventually, or we won't, and that will tell us something too. Dark energy is harder. There's no particle to catch. There's no lab experiment that can isolate it. The only way to study dark energy is to measure the expansion history of the universe and see how it changes over time. That requires looking at objects billions of light years away and measuring tiny differences in their brightness and redshift. The measurements are difficult, the error bars are large, and every new survey seems to deepen the mystery rather than solve it. But the measurements are improving. The James Webb Space Telescope is imaging distant supernovae with unprecedented clarity. The upcoming Vera Rubin Observatory will survey the entire southern sky every few nights, cataloging millions of galaxies and tracking how the universe's expansion rate has changed over the past 10 billion years. New gravitational wave detectors will measure the distances to merging black holes and neutron stars, providing independent checks on the expansion rate. Slowly, painstakingly, astronomers are building a more complete picture of what dark matter and dark energy actually do. And maybe, eventually, we'll figure out what they actually are. Until then, the universe remains mostly invisible. A cosmos where the matter we can see is outnumbered 5-1 by matter we can't. Where the dominant force is not gravity pulling things together, but dark energy pushing them apart. Where the structures we call galaxies and stars and planets are just the visible froth on the surface of an ocean we're only beginning to map. The unseen architects, dark matter and dark energy, built the universe we inhabit and are now deciding its fate. And the fate they're choosing, at least based on current evidence, is expansion. Endless, accelerating expansion, spreading the galaxies farther and farther apart, thinning the universe, cooling it, stretching it, until one day, in the far distant future, the stars go out and the cosmos fades into a cold, dark, empty expanse. That future is billions of years away. But it's coming. The acceleration we see today is the first sign. The universe is not done changing, it's just getting started. The universe is running away from itself. Every second, space stretches a little more. Every galaxy outside our local neighborhood drifts a little farther. The distances grow, the light redshifts. And the expansion, which has been happening for 13.8 billion years, is not slowing down the way gravity says it should. It's speeding up. The cosmos is accelerating into a future that looks increasingly empty, increasingly cold, and increasingly lonely. And the question that has haunted cosmology for the past century, the question that drives every deep field survey and every supernova measurement and every attempt to map the large-scale structure of the universe, is simple. How does this end? The story starts with Edwin Hubble, working at Mount Wilson Observatory in the late 1920s. Hubble was not the first person to notice that galaxies were moving. That discovery belonged to Vesto Slipher, who had been measuring the spectra of spiral nebulae and finding that most of them were redshifted, meaning their light had been stretched toward longer wavelengths. Redshift happens when an object is moving away from you. The faster it moves, the more the light stretches. Slipher found redshifts in dozens of galaxies, and the pattern was clear. They were receding, most of them anyway. The question was why. Hubble added the missing piece. He figured out how to measure the distances to these galaxies. Not easy. Galaxies are far away, and there are no convenient yardsticks stretching across intergalactic space. Hubble used Cepheid variable stars, pulsating stars whose brightness fluctuates at a rate directly tied to their true luminosity. Measure the pulse period, calculate the true brightness, compare it to how bright the star looks from Earth, and you've got a distance. It was painstaking work. Hubble spent years measuring Cepheids in nearby galaxies, building a distance ladder that let him reach farther and farther into space. What he found changed everything. The galaxies that were farther away were receding faster. The relationship was linear. Double the distance, double the recession speed. This was not random motion. This was a pattern, a law. Hubble published his results in 1929, and the law now bears his name, Hubble's law. The speed at which a galaxy is receding from us is proportional to its distance. The farther away it is, the faster it's moving. Not because the galaxy is flying through space, because space itself is expanding. The distance between galaxies is growing, not because they're racing away from a central point, but because the fabric of space-time is stretching, pulling them apart. This is not intuitive. We think of space as a stage, a fixed backdrop where things move around. Hubble's law says the stage itself is expanding. Imagine a rubber sheet with dots marked on it. Stretch the sheet in all directions, and every dot moves away from every other dot. None of the dots are special. None of them are at the center. From the perspective of any dot, all the other dots are receding, and the farther away a dot is, the faster it appears to move. That's the universe. Every galaxy is a dot. Space is the sheet, and the sheet has been stretching for nearly 14 billion years. Hubble's discovery had an immediate consequence. If the universe is expanding, it must have been smaller in the past. Wind the clock backward, and the galaxies get closer together. Keep going, and the distances shrink to zero. Everything was in the same place. The entire universe was compressed into a single point, the Big Bang. Hubble didn't call it that. The name came later, coined by Fred Hoyle in a radio broadcast, ironically while he was arguing against the idea. Hoyle preferred a steady-state universe, one that looked the same at all times, with new matter continuously being created to fill the gaps as space expanded. The Big Bang model, by contrast, said the universe had a beginning, a moment when everything started. Hoyle thought that sounded absurd. He was wrong. The Big Bang turned out to be the only model that fit the data. For decades after Hubble, cosmologists assumed the expansion was slowing down. Gravity pulls everything together. The galaxies are pulling on each other, and that pull should act as a brake on the expansion. The question was whether the universe contained enough matter to eventually stop the expansion and reverse it, collapsing back into a big crunch, or whether it would keep expanding forever, gradually decelerating but never quite stopping. The answer depended on the density of matter in the universe. Too much matter and gravity wins. The universe recollapses. Too little and the expansion continues forever. There's a critical density right at the boundary, and for a long time, measurements suggested the universe was close to that edge. Nobody could tell which side we were on. Then in the late 1990s, two teams of astronomers set out to measure how much the expansion had decelerated over the past few billion years. They used Type 1a supernovae, exploding white dwarfs that have a predictable peak brightness. Because the brightness is known, you can use these supernovae as standard candles to measure distances. Compare the distance to the redshift, which tells you how fast the galaxy is receding, and you can map the expansion history of the universe. Both teams expected to find deceleration. Both teams were measuring how much the expansion had slowed since the universe was younger. The measurements were difficult. Supernovae are rare. You have to monitor thousands of galaxies and wait for one to explode. But by the late 90s, the data was good enough. The results didn't show deceleration. They showed acceleration. The distant supernovae were fainter than they should have been, which meant they were farther away than expected. The universe wasn't slowing down, it was speeding up. The expansion rate today is faster than it was a few billion years ago. And that doesn't make sense. Gravity pulls, it doesn't push. There's no force in the standard model of physics that can drive an accelerating expansion. The teams announced their results in 1998, and cosmology broke. Because the only way to explain what they were seeing was to add something new to the universe. Something that acts like a repulsive force. Something that pushes space apart. Dark energy. Dark energy is now understood to make up about 68 to 70% of the total energy density of the universe. It's the dominant component, more than dark matter, far more than ordinary matter. And it's everywhere. Unlike matter, which clumps into galaxies and clusters and thins out as space expands, dark energy has a constant density. More space means more dark energy. The total amount is increasing every second. And as the universe expands and the density of matter drops, dark energy becomes more and more important. Early in the universe's history, when everything was packed tightly together, matter dominated. Gravity was stronger. The expansion was decelerating. But about 5 to 9 billion years after the Big Bang, the density of matter dropped below a critical threshold. Dark energy took over. The expansion started accelerating, and it's been accelerating ever since. The current expansion rate, measured by observing galaxies in the nearby universe, is about 73 to 74 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies are receding 73 kilometers per second faster. That's the Hubble constant, the number that quantifies how fast the universe is expanding right now. Except there's a problem. When you measure the Hubble constant using the cosmic microwave background, the afterglow of the Big Bang, and run the standard model forward to today, you get a different answer. About 67 to 68 kilometers per second per megaparsec, not 73, 67. The difference is small, but it's persistent, and it's driving cosmologists quietly insane. Two independent methods, same universe, different answers. Either one of the measurements is wrong, or the standard model is missing something. Nobody knows which. The tension between those two numbers is one of the biggest unsolved problems in cosmology. It's called the Hubble tension, and it refuses to go away. Some scientists think the local measurements are biased by the specific sample of galaxies being used. Others think the cosmic microwave background measurements rely on assumptions that might not hold. A third group thinks the discrepancy is real, and it's telling us something fundamental about dark energy. Maybe dark energy isn't constant. Maybe it's changing over time. Maybe the expansion rate was different in the past than the models predict. If that's true, it means dark energy is not a simple cosmological constant. It's something dynamic, something that evolves, and that opens the door to futures we can't predict. The simplest model of dark energy is the cosmological constant, the same fudge factor Einstein introduced in 1917 and later abandoned. A cosmological constant is just a number, a fixed energy density built into the fabric of space itself. It doesn't change, it doesn't dilute, it doesn't interact with anything. It just sits there, pushing space apart with a constant strength. That model fits the data reasonably well. It explains the accelerating expansion. It matches the observations of distant supernovae, but it has a problem. Quantum field theory, the framework that describes the behavior of particles and fields, predicts a vacuum energy density, the energy of empty space itself, and the prediction is wrong by a factor of 10 to the 120th power. That's not a small error. That's the worst prediction in the history of physics. Something is cancelling out most of the vacuum energy, leaving behind a tiny residual that happens to be just the right size to drive the acceleration we observe. We don't know what, we don't know why. It's a coincidence so absurd that most physicists refuse to believe it's really a coincidence. The alternative is quintessence, a dynamic field that changes over time. Quintessence is similar to the inflant field that drove inflation in the first fraction of a second after the Big Bang. The field has energy, and that energy can vary depending on the field's value and how it's rolling through its potential. If quintessence is real, dark energy wasn't always the same strength. It could have been weaker in the past. It could get stronger in the future. The expansion rate would change over time in ways a cosmological constant doesn't allow. Quintessence could explain the Hubble tension. It could explain why the local measurements don't match the cosmic microwave background measurements. Or it could just be wishful thinking. The data isn't strong enough yet to distinguish between a cosmological constant and a slowly evolving field. Both fit, both are possible, and both lead to very different futures. If dark energy is a cosmological constant, the future is grim but predictable. The expansion will continue accelerating. Galaxies outside our local group, the small cluster of galaxies bound together by gravity, will eventually recede faster than light. Not because they're moving through space faster than light, because the space between us and them is expanding faster than light can cross it. They'll redshift into invisibility. Their light will stretch to wavelengths so long we won't be able to detect it. One by one, the galaxies will disappear beyond the cosmic horizon. In a few 100 billion years, an observer in the Milky Way will look up and see a much emptier sky. Only the local group will remain. Andromeda. The Magellanic Clouds, a few dozen dwarf galaxies. The rest of the universe will be gone, unreachable, invisible, forever. The stars will keep burning for a while. New stars will form from the remaining gas in the Milky Way and Andromeda, but the gas supply is finite and it's running out. The universe made most of its stars between 8 and 11 billion years ago, during a period called cosmic noon, when the star formation rate peaked. Since then, the rate has been dropping. Galaxies are using up their gas, they're not making more. In a few trillion years, the last stars will ignite. A few trillion years after that, the last stars will die. Most of them will become white dwarfs, cooling embers the size of Earth, radiating away their heat over billions of years until they fade to black. Some will explode as supernovae, scattering their remains into space. A few will collapse into neutron stars or black holes, dense remnants that will drift through the dark for eons. Eventually, the only objects left will be black holes. Stellar mass black holes from the deaths of massive stars, supermassive black holes from the centers of galaxies, intermediate mass black holes formed from collisions and mergers, and they will not last forever. Stephen Hawking showed in the 1970s that black holes emit radiation, a quantum effect where particle-antiparticle pairs pop into existence near the event horizon, and one particle falls in while the other escapes. The escaping particle carries energy away from the black hole. The black hole loses mass. Slowly, unimaginably slowly, black holes evaporate. A black hole, the mass of the Sun, would take 10 to the 67th years to evaporate. That's a 1 followed by 67 zeros, a number so large it makes the current age of the universe, a mere 13.8 billion years, look like the blink of an eye. A supermassive black hole would take even longer, 10 to the 100 years, maybe more. But eventually, given enough time, every black hole in the universe will radiate away its mass and disappear in a final burst of energy. What's left? Nothing, or almost nothing. Photons, stretched to wavelengths longer than the observable universe itself. A few stray particles drifting through an expanse so vast and so empty that they will never encounter anything else. No stars, no galaxies, no planets, no black holes, just cold, dark, empty space expanding forever. This is the big freeze, the heat death of the universe. The state where entropy has reached its maximum, where every energy gradient has been leveled, where nothing can happen anymore because there's no usable energy left to drive any process. The universe doesn't end in a dramatic collapse or explosion. It just fades, slowly, quietly, inevitably, into a state of perfect, eternal equilibrium. That's the most likely outcome, at least based on current observations, but it's not the only possibility. If dark energy is not constant, if it's a field that evolves over time, the future could be very different. If dark energy weakens, the expansion could slow. Gravity could start winning again. The universe could stop expanding, reverse, and begin contracting. Galaxies would start moving toward each other instead of away. The cosmic microwave background would blue shift instead of red shift. Over billions of years, the universe would collapse back into a hot, dense state, the Big Crunch, the time reverse of the Big Bang. In some models, the Big Crunch could bounce, igniting a new Big Bang and starting the cycle over. A cyclic universe, expanding and contracting forever. Elegant, maybe, but entirely speculative. We have no evidence the universe has done this before. We have no evidence it will do it again, and given that the expansion is currently accelerating, not decelerating, the Big Crunch looks increasingly unlikely. Then there's the worst-case scenario, the Big Rip. If dark energy is not constant, and if it's getting stronger over time, the acceleration will increase. Eventually, dark energy could become so strong that it starts tearing apart structures held together by gravity. First, Galaxy clusters dissolve, the galaxies drift apart. Then individual galaxies are torn apart. Stars and gas clouds scatter, then solar systems. Planets are ripped from their orbits around their stars, then planets themselves. The gravitational binding holding them together is overcome by the expansion, and in the final moments, dark energy grows so powerful it overcomes the forces holding molecules together. Molecules are ripped apart, then atoms, then atomic nuclei. Every structure, every bond, every connection in the universe, undone by the accelerating expansion of space. The universe ends not in a freeze or a crunch, but in disintegration. The Big Rip is speculative. The current data doesn't support it, but it's allowed by the equations. We can't rule it out. The fact that we don't know which future we're heading toward is both humbling and terrifying. We've mapped the universe back to the first few 100,000 years after the Big Bang. We've catalogued billions of galaxies. We've measured the expansion rate to within a few percent, and yet we can't answer the most basic question: how does this end? The answer depends on dark energy, and we don't know what dark energy is. We don't know if it's constant or changing. We don't know if it will stay the same strength forever or evolve into something stronger or weaker. We don't even know if it's a single thing or a combination of multiple effects we haven't disentangled yet. NASA's official statement on dark energy is refreshingly honest. We don't know what it is. We just know it's making the universe expand faster. The uncertainty is frustrating, but it's also what makes cosmology exciting. The universe is still surprising us. Every new telescope, every new survey, every new measurement has the potential to overturn what we thought we knew. The James Webb Space Telescope is finding galaxies in the early universe that shouldn't exist according to the standard model. Gravitational wave detectors are measuring the expansion rate in new ways, adding independent checks that might resolve the Hubble tension or deepen it further. The Vera Rubin Observatory, set to begin operations soon, will survey the entire southern sky every few nights, cataloging billions of galaxies and tracking how the universe's structure has evolved over the past 10 billion years. Slowly, painstakingly, the picture is coming into focus. But even if we figure out what dark energy is, even if we pin down the expansion rate and predict the universe's fate with certainty, the conclusion is the same. The universe is not static. It's not eternal in the sense of unchanging. It's evolving. It had a beginning. It will have an end. And the end, at least based on what we can see right now, is not a bang. It's a fade. A slow drift into darkness and cold, where the stars go out one by one, where the galaxies disappear beyond the horizon, where the black holes evaporate and the last remnants of structure dissolve into a featureless void. It's the opposite of the Big Bang. Not a hot, dense singularity, but a cold, empty expanse. Not infinite energy packed into a point, but infinite space with nothing in it. And yet, for all the bleakness of that far future, the fact remains that we're here now. In the brief window of cosmic history, when the universe is full of stars, when galaxies are still visible, when planets orbit those stars and life, at least on one of those planets, has emerged and looked up and figured out where it came from. That window is narrow. It started about 500 million years after the Big Bang, when the first stars ignited and ended the cosmic dark ages. It will close in a few trillion years, when the last stars fade and the universe goes dark again. We're living in the golden age of the cosmos, the era when the universe is at its most interesting, its most dynamic, its most alive, and we showed up just in time to witness it. Not at the beginning, when everything was too hot and chaotic for complexity. Not at the end, when everything has cooled into equilibrium. But in the middle, when stars are still burning, when galaxies are still colliding, when black holes are still feeding, when the universe is still building structure, even as it tears itself apart through expansion. This moment, this narrow sliver of cosmic time, is the only moment when something like us could exist, and it's the only moment when something like us could look out at the universe and ask what happens next. The answer to that question is still being written. The observations are still coming in. The models are still being refined. The debates are still raging in conference rooms and academic journals and online forums where cosmologists argue over error bars and systematic uncertainties and whether the latest measurement means the standard model is broken or just incomplete. But the broad strokes are clear. The universe is expanding. The expansion is accelerating. Dark energy is driving that acceleration, and unless something changes, dark energy will win, gravity will lose, the galaxies will drift apart, the stars will fade, and the universe, given enough time, will become a cold, dark, empty place where nothing happens anymore because there's nothing left to happen with. That future is billions of years away, trillions maybe. Far beyond the lifespan of the sun, far beyond the lifespan of any star currently burning. But it's coming. The acceleration we measure today is the first symptom. The universe's destiny, written in redshifts and supernova light curves, and the faint hum of the cosmic microwave background, is a long, slow fade into silence. And there is no stopping it, there is no reversing it. There is only watching it unfold, measuring it, understanding it, and accepting that the universe, like everything in it, is temporary. Even the cosmos has an expiration date, and the clock is ticking. The universe is dying, not quickly, not dramatically, not in some cosmic catastrophe that obliterates everything in a flash of light and fury. The universe is dying the way a candle dies when you stop feeding it wax, slowly, inevitably, one flicker at a time, and the process has already begun. We've talked about the near future, the next few billion years, the time when the sun becomes a red giant and swallows the inner planets, when Andromeda collides with the Milky Way and the two galaxies merge into a single elliptical blob. Those events are practically tomorrow on cosmic timescales. They're the opening act. The real story, the one that describes what the universe becomes when all the drama is over and all the players have left the stage. That story takes place on timescales so vast they make the current age of the universe look like a rounding error. We're talking trillions of years, quadrillions, numbers so large that writing them out in full would fill pages and still mean nothing to the human brain, because evolution never prepared us to think in those terms. By the year 1 trillion, give or take a few hundred billion, the last stars will have formed. Not because the universe ran out of space, because it ran out of gas. Star formation requires cold molecular clouds, regions where hydrogen can clump together and collapse under gravity. The universe started with a finite supply of hydrogen, and it's been converting that hydrogen into heavier elements inside stars for nearly 14 billion years. The process is one way. Hydrogen fuses into helium. Helium fuses into carbon, oxygen, neon. Massive stars keep going, building heavier and heavier elements all the way up to iron. Then they explode, scattering those elements into space. But the hydrogen is gone, used up, turned into something else, and the universe doesn't make more. What we have now is what we'll have forever. The remaining gas is being used up, and when it's gone, no new stars will ignite, ever. The stars that are already burning will keep burning for a while. The smallest stars, red dwarfs weighing less than 10% the mass of the sun, burn their fuel so slowly they can live for trillions of years. They'll be the last lights in the universe. Dim, faint, barely glowing, but still there, still fusing hydrogen into helium in their cores. Everything else will have already died. The massive stars, the bright blue giants that light up star-forming regions today, those are already gone in this future. They only live a few million years. They burned out long ago. Medium-sized stars like the Sun, they last about 10 billion years. In a trillion years, they're ancient history. Even the small yellow stars, the ones that could have hosted life, all of them have cooled and faded. The only stars left are red dwarfs, and they're running out the clock. When the last red dwarf finally exhausts its hydrogen, it will contract, heat briefly, and then cool into a white dwarf. A white dwarf is not a star, it's a corpse. A dense ball of carbon and oxygen, about the size of Earth, held up not by nuclear fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons from being squeezed any closer together. White dwarfs don't burn. They just glow, radiating away the heat left over from when they were stars. They start out hot, tens of thousands of degrees, glowing white or blue. Over billions of years, they cool. They fade to yellow, then red, then infrared, then nothing. A black dwarf, a lump of carbon and oxygen sitting in space, radiating no light, no heat, completely inert. The universe today is not old enough for black dwarfs to exist. The oldest white dwarfs are still glowing faintly, but give it time, give it a few 100 trillion years, every white dwarf will cool to black. And that's when the universe enters what cosmologists call the degenerate era. The degenerate era is the age of remnants. No more stars, no more fusion, no more light except the faint afterglow of the cosmic microwave background, which by this point has been stretched by expansion to wavelengths longer than galaxies. The dominant objects in the universe are white dwarfs, neutron stars, and black holes, dead things. Structures held together not by the active processes of fusion or chemistry, but by quantum pressure and gravity. White dwarfs, the cooling embers of low-mass stars. Neutron stars, the collapsed cores of massive stars. Objects so dense that a teaspoon of neutron star material would weigh as much as a mountain. And black holes, the remnants of the most massive stars and the centers of galaxies, regions where space-time has folded inward and nothing can escape. These objects will drift through the dark for a very long time. Galaxies, or what's left of them, will still exist, though they won't look like galaxies anymore. No spiral arms, no glowing nebulae, no bright cores. Just loose collections of dead stars and black holes held together by gravity, orbiting the supermassive black hole at the center. The Milky Way and Andromeda, long since merged, will have settled into a giant elliptical galaxy filled with nothing but white dwarfs, neutron stars, and black holes. No gas, no dust, no light, just gravity and darkness. And then things get strange. Because matter itself, the stuff that makes up white dwarfs and neutron stars and every atom in the universe, might not be stable. Protons, the positively charged particles at the center of every atomic nucleus, are generally considered stable. A free proton sitting in space doesn't decay. It just sits there, forever. At least, that's what we've always assumed. But some theories in particle physics, extensions of the standard model that try to unify the forces of nature, predict that protons are not truly stable. They should decay very, very slowly. The predicted lifetime of a proton in these models is somewhere around 10 to the 34th years. That's a 1 followed by 34 zeros. A timescale so long that no proton in the observable universe has decayed yet. But if the theories are right, given enough time, every proton will eventually break down, splitting into lighter particles like positrons and neutrinos. If protons decay, the consequences are total. White dwarfs are made of carbon and oxygen, elements whose nuclei are built from protons and neutrons. If the protons decay, the nuclei fall apart. The white dwarf slowly evaporates, one particle at a time, over trillions of years. Neutron stars are even worse off. A neutron star is held together by neutron degeneracy pressure, a quantum effect similar to the one that holds up white dwarfs. But neutrons are only stable inside a nucleus. A free neutron decays into a proton, an electron, and a neutrino in about 10 minutes. Neutron stars avoid this because the neutrons are packed so tightly that there's no room for them to decay. But if protons themselves are unstable, neutron stars will slowly lose mass as their protons decay and the neutrons follow. Over unimaginable timescales, the neutron star shrinks. Eventually, it collapses entirely, either evaporating into radiation or collapsing into a black hole. The same fate awaits everything else. Planets, asteroids, comets, dust grains, all of it is made of protons. If protons decay, all ordinary matter eventually breaks down into radiation and light particles. The degenerate era doesn't end in a freeze. It ends in a slow-motion evaporation, where every structure made of atoms quietly falls apart, leaving behind nothing but photons, neutrinos, and electrons drifting through an ever-expanding void. The timescale for this is staggering. Proton decay, if it happens, takes something like 10 to the 40 years to dismantle the universe. That's 100,000 trillion years. The current age of the universe is about 14 billion years. The ratio between 14 billion and 10 to the 40 is incomprehensible. If the universe's current age were a single second, the time until proton decay would be longer than the current age of the universe by a factor of a billion. But proton decay is not certain. We've never observed it. Experiments have been running for decades, massive underground tanks of ultra-pure water surrounded by detectors, waiting for a single proton in a single water molecule to decay and produce a flash of light. Nothing so far. The lower limit on the proton lifetime is currently about 10 to the 34 years, meaning if protons decay faster than that, we would have seen it by now. We haven't. That doesn't mean protons are stable forever. It just means if they decay, it's slower than we can currently detect. The theories that predict proton decay are speculative, extensions of the Standard Model, not the Standard Model itself. It's possible protons are truly stable. It's possible the universe will be full of white dwarfs and neutron stars forever, or at least until something else happens to them. That something else is black holes. Because even if protons don't decay, even if white dwarfs and neutron stars sit in space forever, black holes will eventually eat everything. Not quickly, not through some dramatic feeding frenzy. Black holes grow by accreting matter that wanders too close. A white dwarf drifting through space might eventually, over trillions of years, pass close enough to a black hole to be pulled in. A neutron star in a binary system with a black hole will gradually spiral inward as it loses energy to gravitational waves, eventually merging with the black hole. Even objects that start out far from black holes won't stay far forever. Gravitational interactions, close passes with other objects, random orbital perturbations, all of it slowly stirs the remnants of galaxies. Over long enough timescales, every object in the galaxy either falls into the central supermassive black hole or gets flung out into intergalactic space. The galaxy evaporates. Half the mass falls in, half gets ejected. What's left is a single black hole sitting in empty space, surrounded by nothing. This process takes about 10 to the 20 years, 100 billion years. By that point, the observable universe will be a sparse collection of black holes, some of them stellar mass, most of them supermassive, the remnants of the galaxies that used to fill the cosmos. And then the black holes themselves start to die. Stephen Hawking proved in the 1970s that black holes are not truly black. They emit radiation. The process is quantum mechanical, happening right at the event horizon. Particle-antiparticle pairs pop into existence out of the vacuum, a normal quantum fluctuation. Normally, the pair annihilates almost immediately, but near a black hole's event horizon, one particle can fall in while the other escapes. The escaping particle carries energy away from the black hole. The black hole loses mass. Slowly, particle by particle, the black hole evaporates. This is Hawking radiation, and it's real, at least according to every calculation and theory we have. The problem is, it's insanely slow for any black hole larger than microscopic. The rate of evaporation is inversely proportional to the black hole's mass. Small black holes evaporate quickly. Large black holes evaporate slowly. A black hole the mass of the Sun would take about 10 to the 67th years to evaporate. That's a 1 with 67 zeros after it. Write it out and it fills a line. Try to comprehend it and your brain gives up. A supermassive black hole, the kind sitting at the center of galaxies, weighing billions of solar masses, would take 10 to the 100 years, maybe more. That number is called a googol, and it's so large that there aren't enough particles in the observable universe to count to it. The universe will be unimaginably old by the time the last supermassive black hole evaporates. And when it does, it will go out not with a whimper, but with a flash. The final moments of a black hole's life, when its mass has shrunk to nearly nothing, are violent. The evaporation rate increases as the black hole gets smaller. In the last fraction of a second, the black hole radiates away its remaining mass in a burst of high-energy particles and gamma rays. A tiny, bright explosion in the darkness. And then nothing. The black hole is gone. When the last black hole evaporates, the universe enters the dark era. This is the final state. No stars, no planets, no black holes, no atoms, if protons have decayed. Just a thin soup of photons, neutrinos, electrons, and positrons, spread across a volume of space so vast that the average distance between particles is greater than the size of the observable universe today. The temperature of the universe is a fraction of a degree above absolute zero. The cosmic microwave background has been stretched by expansion to wavelengths longer than galaxies. There is no structure, no clumps, no regions where anything interesting is happening. Just empty space, expanding forever, cooling forever, fading forever. The dark era is not truly dark because there are still photons, but they're so sparse and so low energy that calling it dark is generous. If you could somehow exist in the dark era, which you couldn't because there's no matter to build you out of, you would see nothing, no stars, no galaxies, no glow, just perfect, endless blackness in every direction. The photons are there, but they're moving past you at wavelengths so long they wouldn't register as light. They'd be radio waves stretched beyond imagination, and they'd be so rare that you might wait billions of years between encounters with individual photons. This is the heat death of the universe. The state where entropy has maximized, where every energy gradient has been leveled, where nothing can happen anymore because there's no usable energy left to drive any process. Thermodynamics wins. The second law, the one that says entropy always increases, has run its course. The universe has reached equilibrium. And equilibrium in thermodynamics, is another word for death. The timescale for reaching the dark era depends on whether protons decay and how long black holes take to evaporate. The numbers range from 10 to the 40 years if protons decay quickly, to 10 to the 100 years if we're waiting for the largest black holes to evaporate. Either way, it's so far in the future that the current age of the universe, 14 billion years, is literally nothing by comparison. If you compressed the entire future of the universe, from now until the Dark Era, into a single year, the time humans have existed would be less than a microsecond. The time since the Big Bang would be a fraction of a second. Everything that has happened so far, every star that has ignited, every galaxy that has formed, every civilization that might have risen and fallen, all of it happens in the first instant of January 1st. The rest of the year is waiting, watching the remnants cool, watching the black holes evaporate, watching the universe fade into darkness. And here's the part that breaks your sense of scale. The Dark Era doesn't end. There's no event after it, no reset button, no big crunch to collapse everything back into a singularity and start over. The universe just keeps expanding forever. The photons keep redshifting, the distances keep growing. The temperature keeps dropping, asymptotically approaching absolute zero, but never quite reaching it. Infinity is a long time. The universe has infinity to work with, and it's going to spend all of it in the dark. Cosmologists have tried to find loopholes, maybe vacuum decay, maybe the universe isn't in its lowest energy state, maybe there's a lower state, a true vacuum, and the current vacuum is metastable. If that's true, a bubble of true vacuum could nucleate somewhere, expand at the speed of light, and rewrite the laws of physics as it goes. Everything inside the bubble would be destroyed, not by heat or force, but by having the fundamental constants change. The electron mass might shift, the strength of the electromagnetic force might change, chemistry would stop working, atoms would fall apart. The bubble would sweep through the universe, erasing everything, replacing it with a new set of rules. That would certainly end the Dark Era. It would also end everything else. Vacuum decay is the ultimate existential threat, and the terrifying part is we have no way to predict when or if it will happen. It could happen tomorrow. It could happen in 10 to the 100 years. It could never happen. The universe could be stable. We don't know. Another loophole is quantum tunneling. Even in the Dark Era, quantum mechanics still applies. And quantum mechanics allows for extremely unlikely events given enough time. A white dwarf, if it still exists and protons haven't decayed, could quantum tunnel into a black hole, just randomly. The probability is absurdly small, but it's not zero. Given enough time, 10 to the 1,000 years maybe, even the most improbable events become inevitable. White dwarfs could collapse into black holes through tunneling. Those black holes would evaporate via Hawking radiation. The process would repeat. The universe would flicker with brief bursts of activity, separated by unimaginable stretches of emptiness. But calling that activity is generous. It's not life, it's not structure. It's just random quantum noise playing out over timescales that make eternity look short. And then there's the most speculative idea of all: Boltzmann brains. If the universe lasts forever and quantum fluctuations never stop, then eventually, by pure chance, a random fluctuation will assemble a functioning brain, complete with memories, thoughts, and the sensation of existing. The brain would exist for a fraction of a second before dissipating back into the vacuum. But in that fraction of a second, it would experience something. It would think it had a history. It would think it lived in a universe. And statistically, if you wait long enough, Fluctuations that produce a single brain are far more likely than fluctuations that produce an entire universe full of structure and history, which raises an uncomfortable question. If Boltzmann brains are possible and the universe lasts forever, then the vast majority of conscious experiences in the history of the cosmos will be Boltzmann brains. Fleeting, random, disembodied thoughts flickering in and out of existence in the dark era. And you, sitting here reading this, are statistically more likely to be a Boltzmann brain than a real person in a real universe. The fact that you have a coherent history, that the universe around you makes sense, is evidence against the Boltzmann brain hypothesis. But it's not proof, it's just probability. And probability, over infinite time, does strange things. These are the ideas physicists entertain when they think about the far future. Not because they're likely, because they're the only things left to think about. The universe, given current observations, is heading toward a state where nothing happens. The dark era is the default, the end state, the final answer to the question of what happens next. And the answer is nothing. The universe doesn't collapse, it doesn't reset, it doesn't explode, it just fades. Slowly, quietly, over timescales so long that the word long loses meaning. And when it's done fading, when the last black hole has evaporated and the last photon has redshifted into oblivion, what's left is a cold, dark, empty expanse where the temperature is a fraction of a degree above absolute zero, the density is effectively zero, and nothing will ever happen again. This is not a guess. This is the logical conclusion of the laws of physics as we understand them, played forward over timescales limited only by mathematics. Entropy increases, energy spreads out, gradients flatten. The universe evolves toward equilibrium, and equilibrium is a state where nothing moves, nothing changes, nothing happens. The second law of thermodynamics is not a suggestion, it's a law, and it applies to the universe as a whole. The universe had a beginning. 13.8 billion years ago, everything that exists was compressed into a hot, dense state and then exploded outward. For the first few 100 million years, the universe was dark, then stars ignited. Galaxies formed, structure emerged. For a brief window of cosmic time, roughly 10 billion years, the universe was interesting. Full of light, full of activity, full of stars and planets, and the possibility, at least on one small world orbiting an unremarkable yellow star, of life. That window is closing, the star formation rate is dropping, the galaxies are spreading apart, the expansion is accelerating. In a few trillion years, the last stars will fade. In 10 to the 100 years, the last black holes will evaporate. And after that, there's nothing left but the dark era, stretching forward into infinity. We're living in the golden age, the brief moment between the Big Bang and the heat death when the universe is full of stars and light and the possibility of something interesting happening. It won't last. It can't last. The laws of thermodynamics won't allow it. But it's here now, and we showed up just in time to see it. Not at the beginning, when everything was too hot and chaotic for complexity. Not at the end, when everything has cooled into darkness. But in the middle, the only time when stars are burning, when galaxies are colliding, when planets are forming, when life, at least once, emerged and looked up at the sky and asked where it came from and where it's going. The answer to where we came from is the Big Bang. The answer to where we're going is the dark era. And the time between those two moments, the time when the universe is awake and alive and doing something, is a tiny sliver of its total existence. A flash of light in an eternity of darkness. We're the flash, and it's already fading. You started this video knowing almost nothing about the universe. You're ending it knowing just slightly more. And that gap, that razor-thin sliver of understanding between total ignorance and absolute certainty, is the only place humans have ever lived. It's the only place we'll ever live. We traced the universe from nothing to everything, from a singularity that breaks every equation we trust, to stars igniting in the dark, to galaxies weaving themselves into filaments, to planets forming in the rubble of dead suns, to black holes bending space-time into shapes that make clocks run backward, to invisible forces holding galaxies together and tearing the cosmos apart, to an ending so cold and so empty that even the concept of time loses meaning. And through all of it, one fact remained stubborn and unavoidable. Most of the universe is hidden. Most of it doesn't interact with light. Most of it we'll never touch, never see, never fully understand. Dark matter outweighs us 5-1. Dark energy dominates everything. The visible universe, the stars and planets and galaxies we photograph and name and build myths around, accounts for 5% of what's actually out there. 5%. We are a minority report filed in the margins of a cosmos we barely comprehend. And yet here we are, stardust arranged into a configuration capable of tracing its own origins. Atoms forged in supernovae that died billions of years before the sun existed, now asking where they came from. Carbon and oxygen and nitrogen and iron pulled from the wreckage of exploded stars, assembled by chance into molecules, cells, organisms, brains complex enough to look up at the night sky and map the structure of space-time itself. You are not in the universe. You are the universe, briefly awake, staring at itself in the mirror, trying to figure out what it's looking at. The cosmos doesn't care that you're here. It's not hostile. It's not benevolent. It's indifferent. Gravity pulls. Entropy increases, stars burn until they don't, black holes evaporate. The expansion accelerates. None of it happens for you. None of it happens because of you. You're an accident. A beautiful, improbable, temporary accident in a universe that will keep expanding long after every trace of your existence has dissolved into the background radiation. But you're here now. And right now, in this brief flicker of cosmic history, when stars are still burning and galaxies are still visible and the universe hasn't yet faded into the dark era, you have the tools to ask the biggest questions existence allows. Where did we come from? Where are we going? What are we made of?